So I had a couple of requests over lunch. One was to do some code and show you on code how some of these things work. So I've pulled up an R file that I have that I can send to people I can go over. Another request was to leave some time for questions so people could ask about some projects they're working on and how they're working out. And then the third option is just to continue on with the slides. So what would people like to do? What would you at this point? Yeah, so I mean, I can continue on with the slides. Why don't we do this? I'll do slides for this session, and then after break, I'll do a little bit of R, and then let's see where we are. And so we may not get to the later sections, but we'll see how far we can get. Okay, so we're up now to meta-regression. So what is meta-regression used for? Meta-regression is used when you have heterogeneity, and you want to figure out to what causes to ascribe that heterogeneity. So it's like any kind of regression program. It's just that you're relating the effect sizes that you're estimating to covariance. For example, you might see that the mean differences are bigger in studies with more men and smaller in studies with more women. So get rid of this little thing here. So I'm going to try to explain to you here how we can explain heterogeneity using meta-regression with study level factors, to contrast meta-regression analysis to just analyzing subgroups, and then to also describe some of the limitations of meta-regression. The main limitation is just that the sample size, again, is the number of studies, and so you just don't usually have a lot of data to do these regressions with. Whoops, back to that again. Right, this worked yesterday. I did, but okay. So remember we looked at this, so we did this a little bit briefly yesterday, so this will be a quick review. If you remember, this was a group of studies. I think there were 69 studies or something like that, looking at the use of thrombolytics, clot-busting drugs, to reduce mortality among patients who have heart attacks. And so the left-hand side here is a forest plot of all the studies. And to the left here, it favors the treatment, and to the right favors the control. And you can see that in general, the effects are a little bit bigger over here than they are down here. And in fact, if you accumulate the effects across the studies, you can see that the average, which starts here for this study, and then it goes to here when you accumulate the first two studies, and then to here when you accumulate the first three studies. So each of these points here is the result of a meta-analysis using all the studies that are above it. You can see that this is trending toward the null here. And in fact, the effects are bigger at the beginning than they are at the end, which means basically that these studies here have bigger effects than these studies down here. In fact, you can see that because these are basically sort of evenly grouped around the null value, whereas these are all positive studies. Okay, so what we said was that these studies showed more effect in these studies, and that showed more effect in these studies, and these showed a bigger effect in those studies. And we said that this was grouped by the time to treatment, the idea being that if you got people to the hospital really quickly, these drugs worked much better than if you took a long time to get them. And the basic idea is that if you're giving a drug to save someone's heart muscle, it works a lot better if you get it before the heart muscle all deteriorates, right? If it's once it's deteriorated and it's infarcted, then you're not going to be able to save much of it. And so the idea here was that we could plot all these effects. We could take an average of the study effects in each of these categories, and we could summarize them this way and show that the effects are bigger here than they are here, than they are here, than they are there. And in fact, if we wanted to, we could regress the average effects or the effects on the mean time to treatment, and we could get a regression. And in fact, here, if we fit a regression, it would fit something like this. And you can see that we would be able to describe the effect of the treatment relative to the amount of time it took until you got to the hospital. So the odds ratio is about 0.7 here, and it's about 0.9 here. And so as the time is increasing, the risk benefit is decreasing. So that's the basic idea behind meta-regression. You're relating the treatment effects, in this case, the odds of having a heart attack or of dying, to a covariate, which in this case is mean time to treatment. So another way to do this is it would be tempting to compare the effect estimates between the subgroups by looking at the results from each subgroup separately. And the problem, of course, is that you don't then have a statistical test to see whether this trend is actually significant or not, because all you have are these separate effect estimates. So we want to embed this into a regression format where we analyze all the data together in order to be able to calculate a slope and estimate a confidence interval. So here's an example for the relative risk of dying from breast cancer in screening versus control. This is that meta-analysis I showed you earlier. So in this particular study here, there's 21,000 people who are randomized to the screening group, and a little fewer more, about 21,100 or 200 to the control group. These are the number of deaths from breast cancer in each group, and here's the relative risk. And so you can see the relative risk in the Mānoa study is 0.96, in the Kansas study it's 1.08, and the overall relative risk is 1.04. Whereas in these 6 studies, if you combine them together and do a meta-analysis, the odds ratio is 0.75. And so this is not an arbitrary grouping of studies. This is a grouping, I think, by these people saying that they randomized the people adequately and these guys didn't randomize people adequately. As I was saying, there is disagreement as to whether these studies were well done. And so they claimed that the reason that they found no effective screening was that their study was actually better done. And in fact, these guys had sort of cheated on the randomization, and that's why they were finding these big effects, because people were aware of their results. So there's a lot of different ways you can group the studies. But in this case, if you really did believe that these 2 studies did the randomization properly and these 6 didn't, how would you compare this 1.04 that's 0.75? So one thing is you could just sort of eyeball it, and you could say, well, these confidence intervals don't even overlap, so clearly they're different. But if you actually wanted to do a statistical test, you'd want to put them all together and do some sort of a regression model. So here's an example where we're looking at the effect of exercise on reducing depression, and the outcome here is a standardized mean difference. And so you can sort of think of these numbers here as standard deviation units. So this study, for example, is centered at about -1. That means that in this study, the exercise group reduced the depression by about 1 standard deviation. And so, we're looking at these studies and we see there's quite a bit of heterogeneity. These 2 studies have pretty big effects. This study has a null effect, and these studies are sort of in the middle. It turns out that these studies can be stratified in terms of the amount of time it took for the data to be collected. In other words, how much follow-up was done in each study. And so the first few studies had more than 8 weeks of follow-up, and the other 5 studies had 4 to 8 weeks of follow-up. And if we do this, and we did 2 separate meta-analyses of these 2 subgroups, we would get these 2 estimates. And so the question would be, are those different? Now here it's very difficult to tell because they certainly overlap and they look pretty close together, and you might actually think that there's no difference there. But again, without a proper statistical model, you don't have any way of really testing that. So you could fit a model where you regress the treatment effect on the follow-up time. And in this particular example, these studies had 12 weeks of follow-up. These have 10, these have 8, these have 6, and this one has 4. And you can fit a line there. And the line has a slope of 0.18. And so the standardized mean difference here decreases by 0.18 for each extra week of treatment. So in this case, there is a statistically significant difference. The p-value is 0.008 and the confidence interval is 0.02 to 0.34. And so you might say that the exercise works better the longer you do it. That wouldn't have been obvious from this picture here because this just grouped it into 2 groups. And you can see from the 2 groups, there's no way of doing a statistical comparison, but B, they're much closer together. And it's not clear that this one here, for example, was the longest follow-up. And so therefore, when you fit the line, you're not just grouping all these together, but you're actually using the exact time of follow-up. All right, so in general, those are a couple of examples of meta-regression. It's a way of investigating sources of heterogeneity. So in that particular example with exercise, we found heterogeneity in the effect estimates, and we related it to a factor, and that factor was time on treatment, or time that you were practicing, time that you were doing exercise. And we found that the longer you practiced, the bigger the effect was. So we're relating the study characteristics to their effect sizes. Right, the study characteristics are in this case, is the design of the study, the length of follow-up. And so what we're doing here is we're identifying correlations, right, between the treatment effects, the outcomes, and the covariates of interest, the predictors. Now, because the outcome here is actually an effect size, it's a calculated difference between two groups. In essence, if you did this as a regression model, this is really estimating interaction, right? This is the interaction between treatment and the covariate. So if you have your individual data, then the meta-regression estimate is the same as the treatment effect interaction. And so the correlation, a positive correlation here, implies that you have interaction. You can do these kinds of analyses with either the individual participant data or the aggregated data. In this case, we had the aggregated data by study. And in that case, the unit of analysis is the individual study. We have 9 data points to do our regression with, 1 for each study. And the covariate has to be at the study level, means that rather than having the follow-up that each person in each study had, we have the average follow-up in each study as the variable. So it's a study level variable, not a person level variable. So what are some of the problems we could address with meta-regression? One is, does the intervention work better if it's given longer? Are smaller odds ratios observed in high-risk populations? Is inadequate allocation concealment associated with a larger effect estimate? Is A better than B when each has only been compared with C? So you're basically looking at differences between groups or between subgroups that are defined by study level factors. Question?
The previous slide, it looked like the longer follow-up, the less good one.
Yeah, in this case, right. Okay, you're right. You're right. My mistake. Yes. If you follow up the longer follow up, you have less of an effect. Right. Now, I suspect that is because the treatment was probably only given for 4 weeks, and then they had additional follow up beyond that. So in other words, these are people who are being evaluated right after they end the treatment, and these are people who have longer follow up, which means they probably went some time without actually getting any treatment, and so the effect dropped off. Thanks. Was there another question? Same one. Okay. Yeah, sorry. Okay. I'm glad you caught that. All right. So if we think about the meta-regression now, the unit of analysis is the individual study. And the study effect now, the theta i's that we've been talking about, is now no longer a single value, but it's a function of predictors. And this is just now a regression model where we have a bunch of x's that are predictors, and we put this into a regression. And the factors here, the x's, can either be study level or subject level, or we could use the baseline risk level if we wanted to. We could regress on the control rate. So the factors in a meta-regression are either study level, which means covariates that relate to trial characteristics or to trial participant characteristics, which have been aggregated at the trial level and for which individual participant data are not available. For example, it could be a design feature of a study where everybody in the study has the same variable, the covariate. For example, if it's a blinded study, then everybody's blinded, right? Assuming that the blinding works. And therefore, what you're comparing are studies that are blinded with studies that are unblinded. Or if it is something related to a dosage, and everybody gets the high dose or everybody gets the low dose. So you're comparing high dose studies with low dose studies. For variables which are actually differing at the patient participant level, like age or sex or education level, then what you typically have to do is aggregate those, right? So it would be the average age of people in the particular study, or the percent that are male. Now, there's other covariates that are related to participants and which are like age and sex, which vary at the participant level, and which are subject level covariates. And those you cannot address in meta-regression with study level data because you don't have those data at that level. You would need the individual participant data to do that. So if I wanted to relate the effect for each person to each person's age, then I need the individual participant data, and that's one of the advantages of having that. Yeah. Yes. Right. Right. So if you actually had those subgroups in every study, then you actually could do that analysis. You could actually kind of look at the interactions by study, and you could combine across the interaction effects. Yeah. So this is a typical kind of plot that's used in meta-regression. It's called a bubble plot. Basically, you plot the odds ratio for each study, let's say, against the covariate, which in this case is the reduction in cholesterol in that study, and then you draw a line through the data, and the size of the bubble is related to the size of the study. So the bigger bubbles are the bigger studies, and since these are weighted regressions where you're weighting by the study precisions or the inverse of the variances, the bigger studies are getting more weight. So that's why the line may not look like it's running through the middle of the data, because the small points are being downweighted. So for example, if we had the following two scenarios, on the left-hand side, we've got 3 big studies and 6 smaller studies. And we see that if we look basically at the big studies, there seems to be a negative trend. However, on the right-hand side, if we had the same effect estimates, but now the study sizes were just different. In other words, instead of the 3 big studies being these, the 3 big studies were these, now we have a positive trend. So this is the idea that if you weighted all these points equally, then probably the trend goes in that direction. But if you have differential weights because of the size of the studies, the slope could change, right? So the meta-regression is a weighted regression, and so it's going to be weighted however you're doing it. Now, if you're assuming no between study variability conditional on this covariate, then you would be weighting according to the variance, like the common effect model. But if you're assuming a random effect model, then you're going to be weighting more equally. So again, the line you fit here relates to the weights that you're applying to each of these data points. Okay, so in a random effects regression, our observed data say that the study statistics, the yi's, have a mean theta I and a variance vi, and then we say that the theta i's have a mean mu I and a variance tau squared. And so the difference here now is that each study is not drawn from a single normal distribution with a single mean. It's drawn from a family of normal distributions where the means depend on covariates, right? So it's now a regression model. And in the binary case, the counts still are binomial, but now the logit function, the difference between the probabilities, is a function of these different thetas. And they could also consist of covariates as well. So these would be sort of random intercepts, and this would be a fixed slope. And so what we can sometimes do is fit the model with and without the covariates and just compare the variances that we estimate, the between study variances. And if the regression is effective, then we should have reduced that between study variance, right? Because the between study variance without the covariate is all the between study variability. And once we control for the covariate, we reduce that. So if we go back to our bubble plot here and just look at this, the amount of variability here is quite a lot, but if we fit a line to it, then the amount of residual variability is going to be much smaller. So our tau squared would be much smaller. So meta-regression is a form of linear regression. It describes a linear relationship between 2 characteristics, the outcome variable and the explanatory variables. And in this case, as we said, the outcome variable is the treatment effect measure, and the explanatory variable is some summary description of the study. Now, how do you select those explanatory variables or predictors to look at? So this is where the kind of art of it comes in. So basically, if you have a lot of variables, you run into the multiple testing issue of the more variables you look at, the more likely you are to find one of them to be significant. And so there's a great risk of spurious findings. You also have to be aware of prognostic factors. In other words, prognostic factors are factors that predict the outcome, but they don't necessarily predict the treatment effect. Remember, in a meta-analysis, the treatment effect is the outcome. So if I'm looking at mortality as my outcome, in the meta-analysis, the outcome is the odds ratio, which is the difference in mortality between the two groups. So there might be a factor which predicts mortality, like age, but it doesn't predict the difference between the treatment and the control. So it's not actually an interaction effect, it's really a main effect in the regression. The other major problem besides the multiple testing issue, is that in a lot of cases, the variables that you want for the meta-regression are not available to you, they're missing. For example, a study might not report what the average age of the people in the study is, or it might not report what the percentage of individuals who have a certain condition. When you have design variables, like randomization and blinding, those are typically available from all the studies, but then you also often have the problem that most of the studies all have the same type. And so you really can't distinguish any effects because, for example, 7 of the 8 studies are randomized, so there's not very much way you can do a regression comparing a group of 7 with a group of 1. So these are some of the problems that you run into, is that you may have too many variables, but you also may have a lot of missing data on those variables. So some of the other problems here is that because the sample size is the number of studies, usually you don't have a lot of them, and so you have low power. And if you look at a lot of variables in small sample sizes, you might get some false positives. And it's also very difficult to test the models. In other words, these are regression models. So you could do regression diagnostics to see how well the models fit, but since the sample sizes are small, the diagnostics aren't going to be terribly helpful. As I said, data may be unavailable, and that can either be because people didn't report them, or in some cases, it might even be that the variable, at the time the study was published, it was not even clear that that variable was important. So genetic studies are a really good example of that. There's certain effects which are related to genes, but if some of the literature is 20 or 30 years old, there may not be any genetic data recorded. Another problem you run into is sort of a reporting bias problem, which is that if a study does report covariates or interactions, it often will only report the ones that are significant. And so you might have a problem of bias there. Another problem you run into is that since we're using summary level variables in these kinds of study level factors, so let's say the average age is the covariate that we're using, that may not vary very much across the studies, right? There may be a lot of variability in individual ages, but all the studies may have roughly the same average age. And as you know, when you do a regression, when your explanatory variables, your X variables don't vary very much, you can't predict much. Another problem is that people oftentimes want to infer causality. They want to say, like, well, I found a difference between men and women, therefore it works better in men than women. But of course, these are only associations because these are only exploratory analyses. And then the final problem is that the subject level factors can be affected by aggregation bias. So what's aggregation bias? Well, the idea here is that the group averages that you often have to use to describe the study level variable don't represent individuals well. For example, if the variable is related to the percentage of males versus females in a study, and so what you're doing is you're using the percentage of males, for example, as your predictor. And then what you might say is, well, studies with more males have different results than studies with more females. Okay, that's fine. But now if you want to now make the next conclusion, so let's say that the treatment works better in studies with more males than more females. A lot of times people want to jump to the next conclusion that therefore the study works better in females than in males, or males than in females, right? It works better in studies with more males, therefore it works better for males. But that's not necessarily the case, because one variable is the study level variable and one level is the other variable is the individual level variable. And as an example, you could have a situation where studies with more males have some other characteristic, like maybe they were older studies, and studies with more females are newer studies. And so the effect is really the time. At the time, it's not related at all to their gender. Or it could relate to the fact that studies with more males are different in some other way from studies with more females. The other problem is that, as I said, averages have little between study variation. So, for example, let's say you had two studies, both of which the people averaged out to be 40 years old. But one study had an odds ratio of 1, and the other study had an odds ratio of 0.8. So if you did a very simplistic regression here, you would say that the difference in the odds ratios is not related to the age, right? Because the age didn't change, and yet the odds ratios did. But what if I then told you that in study A, which had the smaller effect, none of the people in the study were older than 60. But in study B, 10% of them were older than 60. And I used the percent older than 60 as the predictor. Now I might find a significant result with age. So again, this is a situation where there's probably a nonlinear effect with age, but I'm not going to be able to pick that up with a study level variable. And so that's what we mean by aggregation bias. The events may be concentrated in a high-risk subgroup. So you'd like to be able to construct the group level variable to reflect that high-risk subgroup, but you don't have the information to do that because you don't have the distribution of ages. You only have a summary statistic like the average. So here's an example, a pictorial example of aggregation bias. I have 3 studies, and I've plotted the log odds ratio versus the covariate. And so on the left-hand side, I'm going to do meta-regression with study-level summary of patient-level covariates. And on the right-hand side, I'm going to do a meta-regression with patient-level data. Now, what I've shown you here is the study-level data. So if you looked at this, you might not be convinced, but if you had to guess, you'd guess probably that the log odds ratio is declining with the covariate, right? The slope probably goes in that direction. All right, and that's the slope I would fit. And that may or may not be significant, but that would be the best I could come up with. Now I'm showing you the real data, okay? So these are 3 studies, and there's 3 different shades of whatever color that is. Actually, it looks even worse up there than it does in mine. But you can see that in each case, the slope is, in each study, the slope is actually in the other direction, right? It's this positive slope. So again, this is sort of a paradox because if I look at the summary data, I get a negative slope, but if I look at the individual level data, I get a positive slope. So this is another example of how you can get misled by using summary level statistics. Now, who can tell me why that's happening? It's related a bit to Simpson's paradox that we talked about this morning. Yeah. Right. Right. So the problem here is that so you're interested in the relationship between the odds ratio and the covariate, but there's a third variable here, which is study. And you can see that the covariate mean varies with study, as does the odds ratio. And the problem here is that the studies with the lowest levels of the covariate have the biggest odds ratios in general. And the studies with the highest level of covariates have the lowest levels of the odds ratios. So that induces a negative slope if you just look at the averages. But within study, there's a relationship in the opposite direction. So let's get a little more specific. Let's say let's say the covariate is age, right? And let's say the odds ratio is looking at the relationship between treatment and mortality. And the higher numbers correspond to an odds ratio closer to 1, and the lower numbers correspond to an odds ratio greater than 1. So in other words, the treatment is more effective in the groups with the higher ages on average, and it's less effective in the groups with the lower ages. But the idea is within each study, the relationship goes in the opposite direction. In other words, as you age in each study, your effect gets smaller and smaller. so that the effect is biggest in the younger people in each study, but because the studies differ with respect to their distribution of the odds ratio of the covariates, you get this confounding. So it's very similar to the Simpson's paradox idea that you can't just combine everything together. And so this is one way you can be misled by these kinds of problems. All right, so here's the overall slope you'd estimate in each of these studies, and it's in the opposite direction. Okay, here's another example from a study I worked on a long time ago. So there's 11 studies here, and then there's an overall effect. And what we plotted here, this was a kidney function study, and we were looking at how kidney function declined as measured by GFR. So that's on the y-axis, and the x-axis is the person's baseline urine protein excretion. That means at the baseline of the study, how much protein they were excreting into their urine. The two lines are labeled C and T. Generally, C is the higher line and T is the lower line, so that's the control and the treated group. So within each study, generally you see that the control is sloping up and the treatment is fairly flat. And in fact, if you look at the difference between the treatment and control, that's the treatment effect. So the treatment effect in each study is bigger for higher protein than for lower protein, right? So in each study, there's an interaction between treatment and protein, such that the treatment effect is increasing as the protein levels increase, right? The treatment effect here is 0, but here it's positive. Here it's 0, but here it's positive. Here it's 0, but here it's positive. So in general, there's an interaction within each study, which says that basically the treatment works better if you have more baseline urine protein. However, if we did a meta-regression, we wouldn't have the individual data. We would only have the average protein in each study, and we'd have the average treatment effect in each study. And I've drawn a dotted line, which is really faint here, at the average protein level in each study. It's generally around 2 grams. And you can see that at that level, there's very little difference between the treatment and the control groups. So since the overall average odds ratio in each study is going to be a combination of all the data in the study, and since most of the data are down here, because most people have little protein, the overall average, the overall odds ratio is going to be weighted more heavily toward this lower end. So it's going to be close to 0. And the baseline urine protein is not going to vary too much. So basically, you're going to find no effect when you do the aggregated meta-regression, and that's what we found. So this was an example we published in a paper a few years ago showing that if you did the analysis within study, you got an interaction, but if you did the analysis between study, you didn't find that interaction. Okay, we were lucky here to have the individual data so we could actually do this analysis. So here's another example. Let's say you're looking at socioeconomic status and you wanted to compare the group socioeconomic status to the individual socioeconomic status. So you might have a study where, or you might have a situation where people who have low socioeconomic status perform worse than people with high socioeconomic status. Let's say you're doing an educational study and you want to see what is the result of like kids getting into college relative to what type of background they come from. And you find that the kids who come from the higher incomes tend to get into college more than the kids from the lower incomes, right? That's a fairly intuitive conclusion. But you might do a study where you actually had an intervention and you intervened in the people with in the low socioeconomic groups. And so the studies or the regions with the low status might do better than the ones with the high status because the intervention is targeted to them, right? So in other words, within each study, yes, it's true that you do better if you start off better than if you start off worse in terms of your income. But in the studies which actually had more low socioeconomic status individuals, you might actually find a bigger effect because the intervention was being targeted to them. So that's another example. Another one would be if you're looking at male versus female. In mixed populations, males may differ from females, but in single populations of all males or all females, you also might find that male populations are different from female populations. But these effects are not necessarily the same. So if I compare an all-female study to an all-male study, that is not telling me that and I find differences there, that's not telling me necessarily that males and females are different. It's just telling me that a study with all males is different, getting a different result from a study with all females. So changes in the male-female mixture proportions may have a different meaning than comparison of individual males and females. So those are just some caveats when you're using meta-regression. My experience has been that in most cases, I don't really find any significant results with regression. There are some cases, and I'll show you one when we do the R code, where there's a very famous example of the effect of a tuberculosis vaccine, which actually works better if it's given further from the equator than if it's given nearer the equator. And the reason for that is that the vaccine actually degrades in heat, and so it's not, I guess when it's near the equator, maybe the refrigeration isn't as good or something, or maybe the places where it was given were not as able to preserve it as well. And so that was an important conclusion. But generally, I've not, in my experience, found too many situations where I was able actually to find a covariate that really explained heterogeneity. So, one other point that I've been making throughout the day is this idea of sensitivity analyses. And so I think it's really important to just stress here that you need to look at how your conclusions might vary compared to all these different possibilities. And so meta-regression is one way to assess this, by sort of breaking studies up into subgroups and seeing if they're different by those subgroups. But sometimes you can also do things like excluding each study one at a time to see whether the results change without a particular study, looking at subgroups, making different assumptions about the models, trying different estimators, or trying different metrics. So these are all things that you should probably take a look at just to make sure that your conclusions are somewhat robust to the assumptions you're making. All right, so to summarize this particular section, heterogeneity is a catalyst for exploring treatment interactions. Meta-regression examines the relationship between effects and one or more study characteristics. It should be used and interpreted with caution, though, because these are observational relationships. You may only find the largest effects because you have insufficient number of studies. There's potential confounding and aggregation bias, and there's also potential non-reporting of data. You could use the baseline risk. I didn't talk about this, but you could also use the control rate or the mean level in the control group as a baseline risk variable as well. But you have to be careful there because they're oftentimes correlated. They're correlated predictors, and so you get into these correlated regression problems. Individual participant data analysis is going to be informative, but long and costly, and we'll talk a little bit more about that coming up. And sometimes, though, regression results can be used to design future studies, because if you find effects that differ across covariates, you might want to design your studies with that in mind. Okay, any questions on that section? Okay, how are we doing on time? 1:36. All right. Let's get it. I'll just give you a brief overview here of Bayesian analysis. Just as a quick, just check how many people here have actually studied any Bayesian analysis. Okay, so this may be Greek to some of you, but we'll see what we can do. Okay, so I want to try to tell you here what some of the advantages and disadvantages of a Bayesian approach to meta-analysis, connect the Bayesian model to the 1 and 2 stage models we talked about this morning, and interpret an individual study effect adjusted for the effects of other studies. So the basic idea behind the Bayesian model, and again, this is something that you would typically take in a whole course on, so let's see if I can do this in 5 minutes. So typically in classical statistics, the parameters that we want to estimate, let's say the mean, are assumed to be unknown fixed parameters. And so the statistical inference is based on the estimates of those parameters that we calculate. So for example, if we're interested in estimating a mean, we would calculate the sample mean, and then the sample mean, because it's a combination of observations, turns out to have a distribution, and that distribution can then be used to calculate to make inferences about the true unknown mean. In Bayesian models, the parameters are not fixed unknown constants, but they're actually considered to be random variables. So the mean you could think about it subjectively as you start off with an unknown mean, and you know something about that mean, or you don't know anything at all about the mean. And as you gather data, you learn about the mean. And as you learn about the mean, you become more and more sure about what it is. And so the random variable aspect of it is that there's uncertainty into what you know about the mean. So there's a probability distribution that quantifies this uncertainty, meaning before I start, I might assume, so let's say my random variable is the treatment effect I'm interested in, like the mean difference between two groups. So before I'm collecting any data, I might, from prior knowledge, have some idea. Let's say I've done a bunch of animal studies and I have some idea that the treatment seems to work. So I might say, for example, that I think this treatment is going to reduce the outcome rate by 5% on average, but I'm not really sure about it. It may not reduce it at all. It might reduce it as much as 10%. And so I could describe that uncertainty by a distribution, let's say a normal distribution centered at 5. Now I collect some data, and with that data, I can construct a likelihood, and I can combine that likelihood with my prior distribution. I do some mathematics, and I end up with an updated distribution. Now, let's say the data I collected, the effect was 2%. So I now average the 5% that I had in the beginning and the 2% I have now, and I come out with some weighted average, and now my new guess is that it's actually 3% effect. And I keep doing that. I keep adding data in, and I keep updating that distribution until it gets fairly precise, and I have a pretty good estimate of it. So that's called the posterior distribution. So what I can then do is, once I have the posterior distribution, I can make statements about the probability of hypotheses. For example, if I have a posterior distribution which is centered at 2 plus and minus 1, then I could say, for example, there's a 50% probability that the effect is at least 2, and a 50% probability that the effect is less than 2. Or I might be able to say that there's a 20% probability that's greater than 3, or a 20% probability that's less than 1. And so I can quantify what's the chance that my effect is any particular size. So the nice thing about this is that it provides a unified model that incorporates all the sources of uncertainty. You can put prior distributions on any of your parameters. So we talked this morning about how the variances are often assumed to be known. Well, in a Bayesian model, you could assume the variances are unknown and just put a distribution on them and collect some data. They're nice because they can incorporate complex model structures. So for example, if you have certain parameters that have restricted ranges, or you want to try non-normal distributions, they're fairly easy to compute with using simulation. The other thing is that you can include external information through the prior distribution. So if you believe, for example, that you know something about the treatment effect before you start collecting data, you can use that in your modeling. And in fact, if you have rare events, so if you have a lot of zero cells, zero counts, you could augment that data by prior information, which sometimes is very helpful. And then you can express the results directly in terms of probabilistic statements. So as an example, a cumulative meta-analysis, in a sense, is a Bayesian analysis. So here, I've ordered 30 studies looking at intravenous streptokinase therapy for treating heart attacks, from the earliest study in 1959 to the latest study in 1988. So the left-hand side shows a forest plot of the data, and the right-hand side shows a cumulative meta-analysis where each estimate here is the result of doing a meta-analysis with all the studies up to that point in time. So this study was done in 1963. If I accumulate the first study and the second study, here's my estimate, and here's my confidence interval. If I now add in the third study, this is my estimate, and this is my confidence interval, and so forth. And you can see that by the end here, I have a pretty good idea of what the estimate is and what the uncertainty is. So if you think about this in a Bayesian context, when I do the meta-analysis at this point, the first study is the prior, and the second study provides the likelihood, and so this becomes the posterior. Now when I move to the third study, this posterior becomes the new prior, and I add in the new data, and this becomes the new posterior. And I continue to update it as I go along, and this is what happens to my posterior distribution as I add in more and more data. And eventually it becomes a fairly precise estimate. Okay, so that's one way of thinking about a Bayesian analysis. Yeah?
But you do it in a different
It shouldn't affect the final result, but it will obviously affect the way it's accumulating, right? So again, this is our hierarchical model that we looked at this morning, where the yi's are the observed effects, the theta hi's are the unknown true treatment effects, and the si squareds are the variances. And the difference here, and then we have our second stage model. So this is just a review from this morning. The difference here now is that our parameters are theta and tau squared, and we're not going to consider them to be fixed unknown constants anymore. We're going to assume them to be random variables. So we need to have some sort of uncertainty placed on them as well. And so we put prior distributions on those parameters. We call them hyperparameters because they're parameters of parameters. And so the idea here is that then it becomes a full Bayesian model, right? Because we have the y's are random variables conditional on, the y's are random condition on theta and s. And then the thetas are conditional on, theta i's are conditional, normal conditional on theta and tau squared. And then the theta and tau squared, they have distributions that are conditional on distributions as well. So oftentimes what we'll do is, what do we know about theta? Well, we may not know anything to begin with. So we put what's called a flat or non-informative prior, meaning that theta can be anything. It's just a uniform distribution. It can be anything between minus infinity and plus infinity. So if it's a log odds ratio, it says that we don't know anything at all about it. And then you also have to put a prior on the variance, and that's a little more difficult because there's not a lot of information to inform the variance. And so they're typically things like uniform priors on the variance or on the standard deviation or inverse gammas. And again, if you're studying Bayesian statistics, the reason these distributions are chosen is to make the computations simpler. The problem here is that these inferences are sensitive to what prior you put on the tau squared. So I'll show you an example later of what this looks like once you do some data analysis. And it turns out then that if you look at the posterior distribution of the random effects, so these are the random effects within study. So this is saying, what is my better estimate of the true effect in study I, having looked at study I and looked at all the other studies. And this turns out to be a weighted average of the data from that study plus the overall mean. And the weights are these BIs, which are proportional to these variances. So each study's mean is a weighted average of the observed data yi and the overall mean theta. And to think about what this means is, let's say that I have a study that has a very large effect. So its yi is very big. But on average, all the studies have pretty small effects. So the theta is pretty small. And so, and let's say that study is pretty small, that has the big effect. So do I believe that result or not? So let me show you some data to make this a little bit more concrete. So this is a meta-analysis of 11 studies looking at the effect of intravenous magnesium on treating people with heart attacks. So these 11 studies, I've given you the data over here on the left. So in the Morton study, there were 40 people in the treated group and 1 of them died, and there were 36 people in the control group and 2 of them died. So I can calculate an odds ratio from that, and I get 0.44, and I can calculate a 95% interval, and I get a pretty wide interval because there's not much data there. So if I now asked you, do you believe that this 0.44 is the true odds ratio or not? You might say, I don't really believe that's necessarily good because that's a very small data set. Now here's another study where there's 29,000 people in each group. And so now the odds ratio is 1.06. And if I now asked you, do you think that's the right odds ratio for that study? You'd probably say, yeah, I believe that one because there's so many people in that study that that's a well-estimated odds ratio. So if I now ask the question, well, what is a better estimate for this Morton study than 0.44? And you believe that these studies were exchangeable, meaning that before you looked at them, you thought they could be, they were all coming from the same distribution, then what would you estimate this true effect as? 0.44 you think probably isn't right. Is it 1.06? The overall average of these studies is 0.59. So is it 0.59? And so what you'd probably say is, well, it's probably not as good as 0.44 because it's too small a study and that effect is a little extreme. It's maybe closer to the average of all the other studies. And the average is 0.59, so you'd want to take a weighted average of the 0.44 and the 0.59, and it turns out you get 0.54 by the Bayesian analysis. Okay, so if we go back now to our formula, this is the weight. BI is the weight here, and maybe I should have used WI, but you can see it's a weighted average of this and this, and here's the weight. It's the within variance divided by the total variance. So if this study is well estimated, in other words, it has a small within study variance, it's a big study, then the B is going to be close to 0, and so you're going to be weighting this, the posterior estimate of the study is going to basically be its average, its own effect, right? Because it's well estimated, therefore I believe this, YI. If on the other hand, SI is very large, in other words, it's a small study, so I don't know the variance very well, then this B is going to be closer to 1, and now I'm going to give more weight to the mean. And this is what's called a shrinkage estimator, because I'm shrinking the estimate back toward the mean. So in this case, this is an estimate that's based on little data in the Morton study, so I shrink it back to the overall mean. Whereas in the ASA study, where this was well estimated, I don't shrink at all. And in fact, if we look back here, we can see the Morton, the 0.44 becomes 0.54, which is shrunk toward 0.59. The 1.06 stays the same. It doesn't change at all because you believe that study. Okay. So these are the shrinkage factors, and basically the larger the factor, if the factor is large, if it's close to 1, you believe the overall mean, and if the factor is small, you believe the Y. So larger BIs or shrink more back to the grand mean, and so therefore well-estimated studies with smaller within-study variances are weighted the most, and bigger within-study variances lead to more shrinkage, smaller within-study variables lead to less shrinkage, and increased between-study variance weights the studies more evenly. So if you have a lot of between-study variability, tau squared is big, then B becomes small because tau's in the denominator, and if B becomes small, then you weight these studies more evenly. Because basically, if this is a large number, all these BIs become the same, and every study gets the same weight. Okay. All right. So then, if we had the binary data, we have a log odds ratio model. This is the same model that I showed you before. The only difference now is that we're going to put prior distributions on these parameters because it's a Bayesian model. We put priors on the theta and the gamma as well. And then we would, for example, choose normal priors, and then we would go ahead and do the computations. Now, I obviously don't have time to get into the mechanics of this, and there are a lot of different priors, and I'm going to sort of just skip over this. These are some of the technical details. And this is what some of these distributions look like. The key point is that if you have some software that fits Bayesian models, all you have to do is specify these prior distributions in your data, and it will go ahead and do these computations for you. And typically what we use these days is something called Markov chain Monte Carlo or Gibbs sampling, which allows you to simulate the data from the posterior distribution so that it runs until it converges, until it's drawing from the right posterior distribution, and then you get samples from that distribution. So let's say I draw 10,000 samples from the posterior distribution. I can now use those samples to summarize what the posterior is. So for example, if I get 10,000 draws of theta from the posterior distribution, the average of those 10,000 draws is an estimate of the mean of theta, and the variance of those 10,000 draws is an estimate of the variance of theta. All right, so if you take a Bayesian course, this is kind of what you learn. You learn how to do this. All right, so let's return back to this magnesium example. The reason I presented this is because I mentioned this earlier when somebody asked a question about the difference between the random effects and the common effects estimates, is that in this particular example, if you do the random effects analysis, you get an odds ratio of about 0.6. And if you do the common effects analysis, you get an odds ratio much closer to 1. So you get a very, very big difference depending on which model you use. And the reason is because in this particular study, if you look at the data, this trial is so much bigger than all the others that it dominates the answer. So if you have a common effect estimate, which is dominated by the sample size, this number is going to dominate the answer. And so your average is going to be close to that. Whereas if you do the random effects analysis where the weights are much more equal, then all these studies that have lower rates are going to have much more an effect, and you get an answer that's closer to the is the random effects estimate. All right, so we've sort of seen here how we get these shrinkage estimates. So these are the posterior estimates in each study. These are the posterior probabilities that the odds ratio is less than 1, i.e. that the treatment's effective. And you can see that for most of these studies, these probabilities are fairly high, which means that if you were to carry these studies on to get more larger sample sizes, and if these really were all drawn from the same distribution, then you should expect that most of these studies would come up with a positive result. They would say that magnesium actually is beneficial for people with heart attacks. And the only study that isn't is this one here, and that has such a small probability because it's got so much data that it's very unlikely that that's going to change around to be less than 1. Right. Yeah. Right, so looking at these results here, it's very clear that this study is different from all the others, right? And so this is a kind of a way of assessing heterogeneity as well. Now, it's interesting, it turned out that this is like the first 11 studies. There ended up, I think, being about 23 studies on this topic. And there were 4 or 5 pretty big studies, none as big as others as big as this one. In the end, so people came up with various reasons why the magnesium was seen to be more effective in some studies than others. And there are various hypotheses that were put forward. One of them is that in some of these studies, the magnesium was compared to a placebo or was compared to very little treatment, whereas in other studies, the magnesium was an add-on treatment to other treatments that were already effective. So for example, it's well known that if you give people aspirin, you give people beta blockers, you give people thrombolytics, that you can reduce the risk of a heart attack or of death after a heart attack. So if you add magnesium on to those already effective treatments, then it doesn't give any greater beneficial effect. And so that's what happened in this study here. This was magnesium plus a bunch of other things versus those other things. And what it's showing is that, well, magnesium has no benefit compared to the other things, or it might even have a little bit of harm. In these studies that were much smaller and were done earlier, the magnesium was being basically compared to nothing effective. And so it was the magnesium given in the absence of anything else is effective, but once you give it with other things, you lose that effect. So that's a situation where the control group is different in all these different studies. And so you might actually want to stratify in the control group in terms of what the meta-regression is. There were other hypotheses as well, like how quickly after the heart attack people were treated and so forth, that played a role. Okay, so as I said, from the Bayesian analysis, you can get a posterior distribution of each of the parameters in the model. So what I've plotted here is the treatment effect in each study. So for example, here, this is the Morton study. This is on the log odds ratio scale. And this is a plot of the posterior distribution of or density of the Morton mean. And you can see it's centered at a value of about minus 0.5, which corresponds to this odds ratio of about 0.54. But there's quite a bit of uncertainty, right? 95% of the probability is between about -2 and let's say 0.5, and that corresponds to this probability, 95% posterior probability interval here. The ISIS study, on the other hand, is very sharply peaked because we know this pretty precisely, right? This is centered at a log odds ratio of about 0.06, and it's very precisely estimated. In fact, the confidence limits are between 1.0 and 1.1. So you know that the effect is very much close to between 0 and 0.1 here on the log scale. So you can see the smaller studies are much more spread out. The larger studies are much more peaked. And here's the pooled estimate, which is kind of a compromise between all these. All right. Then the other parameter that we might be interested in is the between study variance. And so that again has a posterior distribution. So what's interesting here is that this is our best estimate of what tau squared is after we look at the data. And you can see that the most likely estimate is pretty small, let's say about 0.02, right? But there's a substantial probability that it's actually out here. And in fact, if you use something like a D'Arsumoni and Laird estimate, you'd probably get an estimate that's close to this maximum. And so it would be a fairly small estimate. And it would ignore all of this probability that the variance was bigger. And so you might actually get quite a different estimate there from the Bayesian estimate, because the Bayesian estimate is averaging over this distribution, whereas the classical estimate is fixing an estimate here and then giving you a posterior or an estimate conditional on that fixed parameter. One other example that I've worked on, this was looking at the use of ACE inhibitors, which are drugs to reduce blood pressure, looking at how they prevent end-stage renal disease in people with diabetes. And so some of my colleagues did a meta-analysis published in 1997 that showed treatment was effective for non-diabetics. Here are the data. These are 11 studies. You have treated and the control. The outcome here is end-stage renal disease. So in this study, 60 people got treatment, and 7 of them ended up needing dialysis, and 61 were in the control group, and 14 ended up needing dialysis. The odds ratio is 0.4. Here's the probability interval. Likewise, the posterior is 0.56. And you read this table the same way as we read the magnesium. But notice here now that all the posterior probabilities for all the studies are close to 1, and all the posterior estimates are very similar, and they're all pooled close to the pooled mean, which means that we got a lot of shrinkage in all these estimates. And that's because most of these studies are pretty small. So there's not a lot of information in any one study. And therefore, the best estimate we get is the overall average, because we're saying that, well, we don't really know each study that well, but overall, we see that there's a fairly big effect. And so therefore, we believe that big effect probably operates in all these studies. Even this one, which had more events in the treated than the control, so it had an odds ratio of 2.7, but after we shrink back toward the mean, its true odds ratio we think is more like 0.6, and this was just a chance finding. So basically the summary here is that the Bayesian analysis provides a lot of flexibility to model complex problems. I haven't really shown you too many complex problems, but the machinery is there to do it. It can incorporate prior information. It's very natural for random effects models. It allows for inference about both overall and study effects. And by using the Markov chain Monte Carlo simulation, you get the full posterior distributions, and that leads to pretty straightforward inferences. Okay, so any questions on that? Okay, let me say something about observational studies. So I got a couple of quick modules here. So we've been talking a little bit about the difference between randomized and non-randomized data. So I want to just say a little bit about some of the biases that might arise from combining non-randomized data. So first of all, observational studies tend to give more heterogeneous results than randomized trials. And part of the reason for that is the randomized trials are very controlled, right? Now, they're done under controlled experimental conditions. So a lot of the factors that could cause things to go wrong are not present. And so therefore, your results are more consistent. So treatment effects will typically vary between studies from differences in things like where the data are coming from, the different designs that are used, the way the data are collected, either looking back in the past or prospectively, the type of analysis that's done, like whether it's adjusted or unadjusted for covariates, whether it's a longitudinal or cross-sectional design, how the exposures are defined, treatments and protocols, how the studies subjects are selected into studies, and the quality of the studies. And all of this may lead to interactions between the treatments and the covariates, as we saw with the meta-regression. So the treatment effects may vary with a lot of these factors. Now, another problem that you run into with observational studies, besides this treatment heterogeneity, is the idea of confounding. So confounding occurs if you have systematic differences between the treatment groups that involve factors also related to the outcome. So remember this morning when we were doing the Simpson's paradox, I said that confounding was basically like a triangle where you have a relationship between your treatment and your outcome, and then you have this third factor there, which is correlated with both and which just kind of messes up their relationship. So the idea is that if you have randomization, randomization balances the treatment and the control group on all factors by definition, and therefore there's no confounding. You can't have a factor that's related to the treatment because the treatment is randomized between the groups. But if the data are not randomized, then you might have confounding because you might have a situation where there is a factor that's unbalanced between the treatment and the control group, and therefore it's also related to the outcome. And so that may lead to an observed treatment effect that poorly estimates the true treatment effect. And so you need to adjust statistically for confounders in models. But the problem with the observational meta-analysis is that the different studies may adjust for the confounders in different ways, or they may adjust for different types of confounders. So for example, if you are combining data across studies that are observational, and one of the studies adjusts for age, and another one adjusts for age and sex, and another one adjusts for history of diabetes and history of heart attack and race and income and age and sex, you don't know whether all those adjusted estimates are similar enough to be combined. Another problem you run into is that some of the variables that some studies adjust for may have been not collected in other studies, so they couldn't adjust for them. And so what you would like to do is you'd like to have the original data yourself, so you could go back and fit the same model on each study, but you don't oftentimes have that. All you have is what they reported. So you have to deal with what you have. And then sometimes studies will report both the adjusted and the unadjusted estimates. And so then it's a question of, well, I could combine all the unadjusted estimates, and now they're all adjusted for the same thing, namely nothing. But now I know there could be some confounding bias, or I could combine the adjusted estimates, but now I know that they're adjusted for different things, and so I don't know if they're really adjusted in the same way. Other problems you might run into is that the exposures may be measured differently in the observational studies, because remember, there's not a controlled protocol. So they may have measured, for example, a variable at different times. You could have misclassification where certain individuals are classified into different groups than they should be. There's a potential selection bias here because how are the people being chosen for the observational studies? Well, they may be chosen based on convenience, like they showed up to your site or to your classroom or to your lab, and so they were the mice that were available for you to analyze, and so they may not be truly representative of everyone. Observational studies are oftentimes have problems with quality control because they're not randomized, they're not controlled experiments, and so if you're just collecting data from people over time, it may be difficult to collect good data. Another problem is that the controls that you use, they may be quite different from the people who get the intervention, right? If you're just doing a natural history study, the people who have the intervention may be very different from the people who don't, because they may have selected to have the intervention. And then finally, you oftentimes don't know a lot about the protocols of these observational studies, because they're, unlike randomized trials, they don't oftentimes have protocols. And so you may not really be clear on whether somebody actually received the right dose, or it was the dose that they were supposed to get, or whether if they were assigned a dose, they actually took it, and so forth. So I don't really have any solutions here other than to say that you have to be careful when you're combining observational data and make sure that you have justification for what you're doing. It's not always as bad as it seems. Some of the data that I showed you yesterday on the C-sections, for example, those were observational data. We took them from cohort studies. And so, they were robust enough and they were adjusted enough for things that we were able to figure out what to do with them. But observational studies definitely have more potential for heterogeneity than randomized trials. The lack of an explicit balancing mechanism between the treatment and control groups may induce confounding. If not adjusted for confounding, you shouldn't probably combine the treatment effects unless you're pretty sure that the confounding isn't going to cause a problem. If you have the individual participant data, that may allow you to reanalyze the data so that you can avoid the confounding and adjust for everything in the same way. And if you use meta-regression with observational data, you may be able to find some factors that are related to these differences. Okay, questions on that? All right, let me do one more and then we'll take a break. So individual participant or patient meta-analysis. So I'm gonna try now to just summarize some of the differences between what to do when you have the summary data and what you have to do when you have the individual participant data. All right, so this is a specific type of review that's often considered a gold standard because you have the individual data on each person. And the idea is you have the same underlying rationale as with other systematic reviews, but you're using the original research data sets. So for example, here's a data set where you have the patient ID, and then you have information about the patients at study entry, and then you have information about the interventions they were given, and then you have some information about some of the outcomes. And this is patient by patient. So now I don't just know kind of what the relationship is, that so many people in the intervention group had this outcome and so many in the control group had this outcome. I know exactly what each patient had in this study. So this can answer questions that study level data can't. So as we talked about aggregation bias, we can now explore treatment interactions or effect modifiers because publications rarely report results by subgroup, and otherwise we're stuck with meta-regression analysis, but we know that can be a problem because all we have is the group level covariate. Now we have the individual level covariate, so now we can look at interactions within study and we can actually combine them appropriately. So as an example, a while ago I worked on a problem where we're looking at a therapy for people who got kidney transplants, and it indicated that the treatment, namely the transplant, was significantly more effective in patients with elevated panel-reactive antibodies, a certain type of biomarker. So if they had this particular biomarker, then they were going to be much more receptive to the transplant. It was going to go much better, right? So this would be an instance where the individual participant meta-analysis actually explains some of the heterogeneity. Now, the individual participant data require a lot of care and effort to put together, but it can have a lot of benefits because it can help assess and improve the data quality. So just as sort of a quick comparison, if you're looking at cost, then the meta-regression is going to be a lot cheaper, but the individual participant is going to be a lot more expensive because you're going to have to put all these databases together, and you're going to have to clean them. Now, in meta-regression, you can only look at study-level factors. In the individual participant data, you can look at both the participant and the study-level factors. The outcomes in the meta-regression, you can only use the outcomes that the studies reported. If you have the original data, then you can use all the outcomes that they looked at, that they collected data on. If you only have study-level data and you're doing the meta-regression, you can't clean any data, right? Because you don't have the original data. You can clean the data, and in fact, some of the analyses I've done, we've actually gone back to the original studies and tried to find some missing values or values that didn't make any sense, because you do sometimes find errors in these databases. In the study level data, you can run into problems about aggregation or ecological bias and reporting bias. With the individual data, you have reporting bias, but you also have retrieval bias. What do I mean by retrieval bias? Retrieval bias is when the studies that I'm able to get individual data on are different from the studies that I can't get individual data on. So in the example I showed you before, I had 11 studies in the IPD, but there were 3 studies that we were not able to get individual data on. So if those 3 studies are systematically different from the 11 that I got data on, then my results may be incorrect. And then finally, you can interpret things only at a study level versus at a person level. So some of the advantages, other advantages of individual participant data is you can improve the data quality because you can include, if you have the data from unreported trials or maybe ongoing trials, you can include those. You can include outcomes that were unreported in the literature, and you might even be able to derive new ones if you wanted to. You will typically have updated follow-up, and you'll also be including participants who might have been excluded from analysis in the paper, but could be included now because you have the original data. Question? Well, if the data are cross-sectional, then you're basically throwing them all together into one database, but you're retaining the study ID so that you'll do a stratified analysis based on the study. Yes, right. Yeah. So it's just like any kind of a multi-level study. For those of you who've done any clinical trials, it's like a multi-center clinical trial, right? You just think of the studies as different centers. The other advantage, besides be able to find some data that you would otherwise not be able to find, is that the data are oftentimes more consistent, because one of the problems that you run into sometimes with the study level data is that the papers may report different variables. So for example, let's say that blood pressure is an important variable, and one of your studies reports systolic blood pressure and the other one reports diastolic blood pressure. But it turns out that both studies collected both variables. So if you had the original data, you have the same variables in each study. If you don't have the original data, you're at the mercy of whatever they gave you. Or maybe in one study, they reported age categorically. They just told you how many people were over 65 and under 65. Whereas if you have the individual data, you could calculate it any way you want. Another thing is that the outcomes might differ in these studies, but it might be possible to standardize the definitions if you have the individual data, because you might be able to recalculate something. Or if you have different scales, you might be able to translate between the different scales if you have the original data, particularly if you have a way of going back and forth between the two. And then finally, you can do detailed data checking. So you can find those people that were missing from the analysis, or you can find the people who or the variables that were missing in your original study. You might be able to do that, or if you found implausible values, you could correct them. You can also improve your data analyses because you don't have to rely on published analyses. You can do your own analysis. You can analyze each study, reanalyze each study, and then use those analyses as your input to your meta-analysis. You can standardize your analysis across trials because you have all the data. You can distinguish between within trial and between trial information. There's an easier way to handle missing data because you actually have the individual observations. And you can look at more complex models because you have the original data. So, for example, you can do time to event analyses because you can reproduce the Kaplan-Meier curves, for example. You can also look at interactions between treatments and effect modifiers because publications rarely report these things by subgroup, and so you can avoid aggregation bias. And it's also easier to do multivariate analyses because you have all the data now from all the outcomes. Some of the problems, though, are that it takes a lot longer and it costs more to do. So the one that we did that I was describing earlier on the non-diabetic patients, we actually combined 11 studies, and it took several years for us to actually get the data, clean the data, talk to the investigators, do the analyses, and so forth. And so you need to be, very careful now. You're getting data from people, so you have to develop agreements about how the data will be shared and who's got authorship and all that kind of thing. You have to check the data and clean the data. It was, very illuminating to me with that study that we did. So one of the first things we tried to do when we got a data set was we tried to reproduce the statistics that were in the paper that was published. So for example, just average the ages, and did we come up with the average age they reported? And you wouldn't believe how many times we couldn't reproduce the numbers that they'd reported in their tables. And so then we had to go back. I remember there was one case where the sample size was 257 or something, but we found 260 IDs in the data set. And we had to figure out, well, where did these 3 extra people come from? And we ended up calling the investigators, and it turned out that, I forget what the final answer was, but it was something like they'd been excluded for some reason, but it wasn't anywhere in the file. And so all those kinds of things. There's some ethical issues here too, because you're reusing data. So if you're working with patient level data, you might have problems with institutional review boards, saying, do you have the permission to give these data out to somebody else? There's various problems with consent forms and so forth. And then, of course, there's the whole politics of collaboration, where people want to be authors on papers and who gets to be an author and so forth. And then there's the problem, obviously, that sometimes you can't get the data because people don't want to give it to you. So sort of as a quick summary here, the IPD can answer questions at the level of the individual that the study level data can't, but they require a lot of care and effort to put together. They can help assess and improve your data quality, and just be aware that the analyses that you get may not agree with the results using the study level data only, because you may in some cases be actually analyzing different variables. Okay, so we're up to multivariate data. Let's take a break now. When we come back, I'm going to do a little bit of R to show you how some of the things that we've been talking about can be done in practice. And then if we should have enough time. I think we've got a couple hours here. I've got multivariate data and then network meta-analysis as the last 2 sections. We can maybe go through those fairly quickly. So should we say 2:30? Okay. So you don't have these. I will send Tammy these slides and we can circulate them. This is an exercise that we've done before in some of the courses, and I thought it might be useful to run it through. So I'm going to be using R, which some of you may be familiar with. And there's a nice package in R called Metaphor, which is a library that you can just load. And so I'm going to use Metaphor to enable us to do the analyses. Can everybody see that? I tried to make it a little bit bigger than it was on my screen. All right, good, okay. So first you load in the library, and then I'm going to use this Bcg data set. So I've loaded that in, and just to see what it looks like. This is the tuberculosis data set I was talking about. And so this is a collection of 13 studies that were done between 1948 and 1980. What they did is they used this BCG vaccine to see whether or not it reduced the incidence of tuberculosis. And so the number of positive cases and the number of negative cases in the treatment group, the number of positive cases, the number of negative cases in the control group. And so from those, we could calculate various statistics. We have the 2x2 tables. We also have 2 covariates. One is the latitude at which the study was conducted. So I think, anybody know what the latitude is here? Is it like 20 something? Yeah, I know back home in Providence, it's around 40 or 42. So some of these studies were done maybe in Europe or Canada or something. And then there's others that are much closer to the equator. They're quite far south. I think some of these were actually done in South America as well. And then the other covariate is whether or not, or how the individuals were allocated to the treatment and control groups. So random means they were randomly allocated. Alternate means that they were alternated between treatment and control. And systematic means there was some sort of non-random allocation that was used. Okay, so the numbers here correspond to a 2x2 table. And so what this program does is it works with the 4 counts in the table and it calls them A, B, C, and D. And so the first command that you used here is called RMA for, what does it stand for? Something meta-analysis. I guess random effects meta-analysis would make sense, right? So now the way R is constructed is that you have a command. So this is the function that you call. And then you have a bunch of arguments here, which are basically giving you the data and the model that you want to fit. So the way we interpret this is we're going to use the odds ratio as our measure of effect. A is the column that's labeled T-pos. B is the column that's labeled T-neg. C is this one, D is that one. We're going to use the REML, or restricted maximum likelihood method, to calculate the between study variance. Our data are in this Bcg file. And then this is just some information about how many digits we want to display, and then what we want to do with displaying the labels, author and year. So we'll run that, and then we can print it out. And so this has done our random effects meta-analysis. So it tells us that K is 13. We have 13 studies. The tau-squared estimator is using REML. Our tau-squared estimate is 0.338 with a standard error of 0.178. Tau, which is the square root of this, is 0.58. Our I-squared value is 92, and our H-squared value, which is sort of a different way of expressing I-squared, is 12. Our Q-test has a statistic of 163, which according to the chi-square test is a p-value of 0.001. So in other words, there's a lot of heterogeneity in the data here. We have an I-squared of 92%, and we have a Q that's very significant. Here is our model estimate. Again, this is on the log odd scale. So our estimate is 0.745 with a standard error. And here's our confidence limits, and it's highly significant. All right. So that is, that's how you do the analysis. Now we're going to actually predict these. So we're going to actually transform these back to the odds ratio scale using the exponential transformation, since this was on the log odds scale. And so this minus 0.745 corresponds to an odds ratio of 0.475. And here's our confidence limit, our confidence interval. So this is the interval for the estimated mean, and this is the prediction interval. So in other words, the odds ratio here is 0.475, and the confidence limits on that are 0.33 to 0.68. And if we wanted to predict a new study, our confidence limits would be 0.1 to 1.6, a little wider because it's for a single study. We can then make a forest plot. So these are using some R commands to generate the plot. And I'll just run the forest command. And need to widen this out a bit to make it readable. Can sort of play around with this. There's various ways of doesn't really display terribly well. See if I can make this any bigger. Okay, so there's our forest plot. These are the weights that are applied to each study. And since I haven't actually run all the commands yet, now the problem is to get this back, I'm gonna have to squeeze this. Let's see, where were we at this point? We just ran the forest command, okay. So we'll, let's see. So then we can add some text on. Okay, so this is our final forest plot. So this is telling us using a random effects model. Those are the random effects weights for each study. You can see they're pretty equally distributed. The odds ratios in each study together with the 95% confidence limit, and then the random effects estimate at the bottom, which is 0.47 with a confidence limit of 0.33 to 0.68. And we can just verify that that's the same as what we had right here. Okay. Yeah. I think so, yes. In fact, I mean, in this program, that's, I think, one of the things that you can vary. So there's a lot of options for the graphics and for the analyses in these programs that, you know, you can basically make it look any way you want. You'll notice, for example, here that the odds ratio is actually on the arithmetic scale rather than the logarithmic scale. You might want to change that to be a logarithmic scale, depending on what you're looking at. I don't think they do. There are other packages like Net Meta and so on that do these kinds of things. I don't think ggplot does. I mean, this was written actually before ggplot, so I don't know whether it's kind of. I mean, it's not. It's been updated, but I'm actually going to see the guy who wrote the program this summer, so I could ask him whether there's, you know, he's working. I mean, he sort of does this on his own, so. Whether, you know, he's actually planning to implement ggplot here. Yeah. Oh, so this is the confidence interval for the predicted mean, and this is the confidence interval for the for a single observation for a new value. Okay, then, so that was just using sort of standard normal methods, right? We used the log odds ratio, we did the weighted average and all that kind of thing. You can also use the binomial likelihood methods, the one-stage methods. And so for that, you need some sort of a mixed model package. So we can use LME4 here to do that. And then we can use the GLMM RMA.glmm command, which calls the LME4 GLMM package using the odds ratio, again, giving A, B, C, and D. We're using, so there are various models here. So for example, if you do help on RMA.glmm, you can get a nice help file. And so, for example, if you wanted to know what models you can actually run here, these are all the different options you have. So the models are um.fs, um.rs, blah, 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 see details. So if you can go down to the details, um.fs is an unconditional generalized linear mixed effect model with fixed study effects. So that's the fixed intercepts model. This is the random intercepts model, um.rs. cm.al is a conditional generalized linear mixed effects model. So that's like the conditional model I talked about. And then this would be a conditional generalized linear mixed effects model using an exact likelihood. So again, different models you can run. So we're just going to run the standard kind of fixed intercept model here. And that's for the fixed study effects. This is with the random study effects. We'll run the um.rs model. And so here are the results we get for the, so for the fixed effects model, we get an estimate of minus 0.745, and we can compare that to the random effects, the model we got with the normal, which was, we got the same answer. The standard error here was 0.186, and the standard error here is 0.176. So that's pretty close. If we run the random study effects model, then our estimates are slightly different. We get minus 0.762, but a standard error of 0.181. We can test for heterogeneity and so forth in the random effects model. We can estimate tau squared. And so this is the between study variance here. You still see there's a lot of heterogeneity. And this is the variance of the study effects themselves, of the intercepts. So this is the sigma squared variance component on the intercepts. this is the variance component on the effect estimates, and you can do a test for heterogeneity. And so basically what this is showing is that no matter how you do this analysis, you have very consistent results. It's pretty robust to the model specification, which is nice. Then another thing we could do is what's called a leave one out meta-analysis. That means that you do the analysis, leaving each study out in turn. And you can see how the results vary with that. So here's the estimate without the Aronson study. Here's the estimate without the Ferguson study, and so forth. And again, there's not a huge amount of variability here, although, you know, between here and here, that's a bit of a difference. But again, all of them are going to be significant. So it's saying that you know, if you leave out one study, you still get the same answer. So it's a fairly robust analysis. Yeah.
So is that analogous to even like a validation?
Yeah, well, it's not a cross validation. So I'm not leaving out one study and predicting it from the other 11 or other 12. I'm just saying if I left one study out and I analyzed the remaining 12, what would I have? Yeah. So it's just a sort of a sensitivity analysis to make sure that there's no outlying study. So for example, if you go back to the magnesium study, if I redid that without the ISIS, it might have given me a very different answer. So it's just telling you, is there one study that's kind of driving the analysis? Yeah. Okay, now I've lost mine. All right, so now we might, let's say we wanted to do a cumulative meta-analysis. We can calculate the odds ratios and run our random effect meta-analysis now. And then we can accumulate it. And here's the cumulative analysis. So if we enter these studies in chronological order, after the Aronson study, that's the estimate. After the Ferguson study, that's the estimate. And you can see that the first few studies had a bigger effect than the last few studies, right? Because the estimate is getting is going towards 0. And then we could do a forest plot of that. So that's the cumulative effects on the forest plot. Okay, then we might want to actually subgroup by some studies. So for example, we could here redo our analysis, now do our forest plot. Separating here by the type of randomization that they did. So the top 4 studies are systematic allocation, then random, then alternate, and we can get a summary estimate for each one. Just run this through. And so now the summary estimate for the systematic allocation is 0.65. The summary estimate for the random allocation is 0.37. And the summary estimate for the alternate allocation is 0.54. So they're all showing pretty strong effects. Notice that this one isn't significant, but that's because there's only 2 studies here. So it doesn't look like the method of randomization has too big an effect on the overall average effect. Now I'm going to run a meta-regression analysis with latitude as the covariate. And so you'll notice here that I have used the command mods equals ablat, which is the absolute latitude. So that's throwing that modifier into the model. And there's the bubble plot, showing that the effect here is the odds ratio is higher when you're at a latitude that's closer to the equator. and it goes below 1 pretty quickly, and then when you're at the high latitudes, it seems to be doing much, much better. You can put a line on that, confidence limits, and there's the null line, right? So, looking at this confidence limit goes below 1 at a latitude that's about 20 degrees. So you might say that as long as your vaccine is given at a latitude of 20 degrees or higher, it's going to work pretty well. So now I could do a model with 2 moderators. I could use allocation and latitude. And here's my regression model. The latitude is significant, but the allocation types are not. All right. So that's kind of a quick summary of some things you can do for these analyses. I mean, there's a lot of diagnostics you can do, and there's obviously a lot of different modifiers you could use. But that's a fairly simple program to run, and it's got nice documentation too. So I think it's pretty easy to use. So I'll send that around to Tammy, and she can distribute that. And if people have questions, let me know. The author of that is Wolfgang Wieckbauer, and he's written a few papers on the software. So he's actually, I've often found that he's really good with answering questions. So okay, let's go back to Okay, so let's head into multivariate data at this point. So far we've been talking about one outcome. What I want to do now is show you how to differentiate between, actually those are the wrong objectives. What I want to do is show you I want to combine the data from different studies. And the multivariate setting either could be multiple covariates, in which case you have meta-regression, could be multiple outcomes, which we haven't really talked about yet, multiple measurement times, in which case you have longitudinal data, or multiple treatments, in which case you have network meta-analysis. And so I want to talk a little bit, just give you a very brief overview of all those areas. All right, so what are the different types of multivariate data we might have? So one is our treatment effects might depend on different covariates. We've just seen that with meta-regression. There's also using the baseline risk as the covariate. In other words, the rate of events in the control group. It might be that the studies which have higher risks have better effects, or studies with lower risk have better effects. Another type of multivariate data is when you have many studies that have many different treatment comparisons. Those treatments form a network. For example, you might compare A to B in some studies, and B to C in other studies, and C to A in other studies, and C to D in other studies. And so that's network meta-analysis. And you could either do that with efficacy studies or diagnostic test studies. Sometimes you have data with multiple outcomes. You might have an efficacy outcome and a harms outcome, or you might have a safety outcome and a benefit outcome. And so that could be analyzed by multivariate analysis. We also could have longitudinal data where you have data at different time points. If you're dealing with diagnostic tests, you might have sensitivities and specificities, which can be analyzed together. You might have other problems where you have outcomes with multiple overlapping categories, like does somebody have disease A, B, or C? And then other cases, you might have correlation matrices that you want to analyze in a multivariate fashion. So what's the basic idea behind multivariate data with outcomes? Well, now I'm going to concentrate on data with several outcomes. So most studies are going to report more than one outcome. They're certainly going to collect data on more than one outcome. And we usually analyze all these outcomes separately and come up with a separate meta-analysis of each one. But we know that the effect estimates from outcomes measured in the same patients are going to be correlated. If somebody does well, on one treatment for one outcome, they're probably going to do well on that treatment for another outcome. So the within study correlation there expresses how much we can learn about one outcome when we know the other. And so the idea is that if you do the meta-analyses one at a time, each outcome separately, you're ignoring that correlation, and so you might be having less power, right? Because you're throwing away some information that you have. And multivariate joint meta-analyses can borrow strength across studies, so they can learn from each other. And this is particularly useful if you have missing information, because that's how you do imputation. So in studies reporting several outcomes, even if the estimates aren't measured on the same people, they can be correlated across studies. So for example, the effect in men and the effect in women might have zero correlation within study, but if the treatment is effective in men, and if sex is not a strong effect modifier, we also expect treatment to be effective in women. So the correlations within a study could either be zero kind of by definition, by structure, because the outcomes are assessed in disjoint groups. So for example, you look at an outcome in men and another one in women, or it could be non-zero for outcomes that are assessed in the same patients. For example, in cancer studies, we often look at overall survival and progression-free survival. So if one is surviving better overall, you're probably not getting your cancer. Longitudinal data, you have repeated measurements taken over time. So if I measure you at 3 months and 6 months and 12 months, those are going to be correlated. When I have competing risks, increasing the risk of one event will decrease the risk of another event. The correlations between structures, between studies, are generally not zero, even if the within study correlation is zero, because we usually have heterogeneity between studies. So one of the problems with the multivariate analyses is it's like the problem that we had early on this morning when we were talking about how to do the effect size when you have mean difference data and you're taking differences pre and post. You need to know a correlation that you often don't have. And so a similar problem arises in multivariate data because you need to know the correlation between the outcomes, but oftentimes the summary reports don't give you those correlations. So you need the individual data, or you need to ask the investigators for those. Sometimes, however, you do know the correlations because there's either structural independence between the outcomes, or there's a probabilistic structure. For example, the categorical data, if you have data that are outcomes that could be one of 3 types, let's say you can be in good health, poor health, or average health, that is technically a multinomial variable, and we know what the correlations of multinomial random variables are. And so therefore we can estimate the correlations from the parameters of the model. In other cases, if we have individual participant data, we can figure out the correlations by just running the correlation matrices. Sometimes what you have to do, though, is you have to just assume correlations and then try different correlations and see if it makes any difference in a sensitivity analysis. Sometimes you can reformulate the question to estimate only a single correlation for a marginal model, adding the within and the between study variance together. So that's a paper that was written a few years ago, which basically said instead of having to know the within and the between, you can make an assumption and just estimate the sum, which you can sometimes do from the data you have. And for the between study correlation, you typically can estimate that from the data in principle, just like we've been doing with our random effects models. So just to look and see what such data look like. Yeah. Mm-hmm. Sure. Yeah, I mean, you could either do it explicitly in a Bayesian model, or you could just, assume that those correlations. Let's say, for example, that generally the correlation between your 2 outcomes is around 0.6. Just assume it's 0.6. Yeah, that's just kind of an imputation in some sense. So, statistically, what's going on here is, let's say that you have, so you have case studies here, and in each study you have 2 outcomes. So Y11 and Y12 are the 2 outcomes in the first study. YK1 and YK2 are the 2 outcomes in the case study. And so I'm going to assume that, let's say that each of these outcomes has a normal distribution. So theta 11 is the mean of y11, and theta 12 is the mean of y12. And then they have a correlation, a covariance matrix. So what we've been dealing with so far with univariate data, we just had a y11, we just had a theta 11, and we just had an S11 squared. That was our variance. Now that we have two outcomes in each study, we have two variances and we have a correlation. Right, so rho W1 is the within study correlation for study 1, rho WK is the within study correlation for study K. And S11 and S12 are the variances, and SK1 and SK2 are the two variances. And then at the between study level, if we have a random effects model, we assume that the thetas are normally distributed around mean theta 1, theta 2, and tau 1 squared and tau 2 squared are the two between study variances for the two variables, and then rho B is the correlation between study. All right. So in other words, in this model, we would have a whole bunch of more parameters than we did in our previous models because we now have two outcomes. So we have double the number of means, double the number of variances, and we have correlations as well. So this can be fairly difficult to fit. If you have individual data, of course, you can always fit these generalized linear models. If you don't have individual data, though, you need these statistics. And in fact, you need the S's and you need the rhos, and you need to be able to calculate theta, and you may not have all that information. So there are a variety of things that have been used to fit these models. And again, oftentimes you assume that the within study variances are known, and either the within study correlations are known or that they can be combined with the between study correlations in some way. So you can use restricted maximum likelihood or maximum likelihood. You can use the multivariate method of moments, generalized least squares. You can use a Bayesian method, and there are various ways of doing that. And I'm not really going to get into the details of that. There's some nice papers, and there are a couple books that cover this. It's just general multivariate, normal theory, and your only difference here is that you're dealing with these summary statistics, and so you can write down the likelihoods as long as you have sufficient statistics. So we and others have done empirical studies sort of comparing what happens if you do the analysis as, let's say, two univariate analyses versus one multivariate analysis, one bivariate analysis. And generally, the estimates are fairly similar, whether you do it as a univariate analysis or as a multivariate analysis. The multivariate analyses had slightly shorter credible or confidence intervals because there's a little bit more information that you're getting from the correlations. The multivariate estimates are confidence intervals are generally shorter when comparing differences in means. The between study variances are a little bit less. The predictive interval is a little bit shorter. But one of the problems is that the between outcome correlations are poorly estimated, and it's not really clear what to do when you have missing outcomes. People have sort of hypothesized that if you analyze them together, you can do some imputation, and that's probably true. But how well that works in practice is not really that clear. Borrowing strength here with the multivariate analysis is sort of optimal when you're missing an outcome in some studies, but you can assume the outcomes are missing at random, or the within or between study correlations are strong. So what are some of the advantages here? That the multivariate models allow you to estimate the parameters in a single model, appropriately counting for correlations and testing for combinations of parameters. And the parameter estimates have better properties and can borrow strength, but this is all dependent on the model, the multivariate model being the correct model. Of course, if it's not a bivariate normal model, or if it's you've got the wrong covariance structure, then you're not going to get better results. It reduces standard errors and bias a little bit relative to separate meta-analyses, and it sort of avoids the multiple testing issue, and it can reduce the problems with partial reporting because you're able to do these imputations. The disadvantages are that the univariate analyses are simpler and easier to understand. The correlations are difficult to find, and sometimes estimate. There's more assumptions, and in particular, assuming normality may introduce inappropriate kind of borrowing of strength. And you can exacerbate publication bias if the available secondary outcomes are assumed to have the same distribution as the missing ones, and they don't. So the take-home message here from the work we've done is, as long as we focus on the point estimates and the confidence intervals for the main effects, the choice between multivariate and univariate meta-analysis it's unclear whether there's practically any importance. But multivariate models using a discrete likelihood, like for binary outcomes, generally result in shorter predictive intervals, but they might be a little bit longer for normal intervals. And basically, the idea is that the multivariate outcomes are not really that useful unless you're looking for combinations of parameters. So if I'm interested, for example, in what's the difference in the effect between the treatment effect for one outcome and the other outcome, the multivariate analysis might be useful because I can't estimate that difference unless I do the multivariate analysis. But if I'm just interested in the treatment effect for each outcome, I might as well just analyze them separately. Okay. And I just wanted to show sort of one couple slides here on longitudinal data, and I'm not going to say much about this, but this is the structure that you might find. You might find that you have 5 studies that report data at 5 different times, but not every study reports all the data at each time. So the first study reports the average effects at 5 different times. The second study only does it every year. The third study only does it for the first year, and so forth. And so you have these missing values, and how do you deal with them? And so the only way to really deal with them is to impose some sort of a model on them, and then use that model kind of as a way to impute the missing values, or at least to work with the likelihood, the observed likelihood that only involves the data that you have. And so typically what we would do is we'd construct some sort of a covariance matrix that would include the within study variances and the correlations. And if it's longitudinal data, we might have a specific structure like an autoregressive structure or a random intercept model that we could use to estimate these correlations. So I'm not going to say much about this. It's very similar to other kinds of multivariate analyses, but the differences here are that you only have summary level data, and so you're only going to be able to fit these kind of models in certain specific situations where the data that you have are sufficient statistics. So in the normal case, you need the means and the variances and the correlations. So the conclusion here is that we have a lot of different types of multivariate problems, and these methods can be more efficient, but they require more assumptions, and we need better methods and better software. I think things are improving. People have been talking about these models now for quite a while, and I haven't seen too many analyses where people actually use these in practice. I don't know whether that's because the software is not available or the data are just not amenable to it, because my experience with most of the data that I've seen is that a lot of times you have a lot of missing outcomes. You might, for example, find a meta-analysis with 30 studies, and you have 5 different outcomes you're looking at, and one of the outcomes you have data from 12 of the studies, and another outcome you have data from 10 of the studies, another outcome you have data from 5 of the studies, and they overlap very little. And so then the problem is, well, how do you do a multivariate analysis when you've got so much missing data, and you don't really know why the data are missing? Because it may very well be that the data are not missing at random because they're missing because they weren't significant, or could be that they weren't collected, but you really oftentimes don't know the reason unless you go back to the original studies and ask the authors. Okay, so let me stop there and see if there are any questions on that very cursory overview of multivariate meta-analysis. Yes. Yeah.
Sometimes you have different parts of that path. And I think back to yesterday, you had some kind of conceptual model set up. And that seems to me a little bit different than necessarily a
Yeah, well, I mean, so that's a situation where you do have multiple outcomes, but they have a certain structure. And so, you know, one outcome is affecting another outcome, but some outcomes don't affect some other outcomes. And so these structures are where all the outcomes can affect each other. Those are situations where you have some constraints. And so, you know, if you look at basic structural equation modeling, I mean, it has multivariate aspects to it, but there are constraints on it. So.
But there are essentially structural equation modeling and meta-analysis.
Yeah, there is actually a book. Mike Chung and a couple of colleagues wrote a book on structural equation modeling and meta-analysis. Yeah, so that's a good, came out about 4 or 5 years ago. It's a good book to look at. I might have included it. I had some book listed at the end. I can't remember if I put it in there or not. Okay, the final topic is network meta-analysis. So this is something which is fairly new. So I want to try to tell you the difference here between direct, indirect, and mixed treatment comparisons to identify and look at the concepts and assumptions of network meta-analysis, such as transitivity and consistency, and summarize findings in common tabular and graphical formats. So what's the motivation for network meta-analysis? Again, this is sort of in a health context, but people oftentimes need to decide which treatment is best. And oftentimes there's more than 2 choices. So we're used to doing meta-analysis where we're comparing 2 things, but oftentimes we have a lot of different choices. For example, you want to know what's the right kind of toilet paper to buy, right? So let's say there's a bunch of studies of different toilet papers. There's more than 2 of them, right? We'd like to be able to say, well, you know, this one is softer, this one lasts longer, you know, whatever. This one costs less. So you can see that's just a very simple assumption. Another one might be you're looking at different treatments for depression. So there might be some SSRIs. There might be 10 of them on the market. Which one should be used? So some other examples would be treatments, different treatments for knee osteoarthritis, different treatments for stopping smoking, different treatments for improving student performance, different ways of modeling something. Unfortunately, most of the time, almost all the time, we're never going to have one study that looks at every option for a variety of reasons. And so if we do meta-analysis of pairs of these treatments, then we reach the issue of, well, how do we come up with an overall combination? If I know that A is better than B and B is better than C and C is better than D, but D is worse than A, you know, in my meta-analyses, how do I put those together? And it can become complicated because remember, each set of pairwise meta-analysis is combining different studies. And so there may be confounding here between study and treatment comparison. So in pharmaceutical studies, in looking at drugs, a lot of companies, to get their drug license, will compare their new drug with placebo or standard care just to show that it's better than nothing, and so that they can get it approved to sell it. So that's great for the company. They get to sell the drug. But then, you know, you get sick and you go to your doctor, and your doctor's trying to decide which of these several drugs that all kind of do the same thing is better for you. And there's no study out there that actually compares the drugs themselves, because the companies have no incentive to do that. So what we're going to try to use is the idea of an indirect comparison to provide useful evidence here. And so I'm going to tell you what an indirect comparison is. And then I'm going to extend that to network meta-analysis, extending the pairwise meta-analysis by combining all the pairwise comparisons across the range of interventions. And therefore, I'm going to incorporate both the direct and the indirect evidence. So here are some examples of network meta-analysis that have been done. Different types of biologics for people with rheumatoid arthritis, different types of treatments for people trying to stop smoking, and different kind of agents for preventing people who have cardiovascular events. So this is a fairly well-known network meta-analysis that was published about 10 years ago. I've been using this for about 10 years. So you've got 12 treatments here arrayed as the vertices of a polygon. These are nodes in a graph. And each line that connects two nodes to two treatments indicates a direct comparison. So for example, if you look at the top, that sertraline, I don't remember what the brand name is. It's compared to fluoxetine, which I do know is Prozac. And that line is fairly thick, which means that there have been a bunch of studies that have compared those two drugs. Likewise, there's a bunch of studies that have looked and compared fluoxetine to venlafaxine and so forth. However, if you look at duloxetine, which is over here, and mirtazapine, which is over here, you'll notice that there's no line connecting those. That means that there's never been a study, or there wasn't up until this time, that actually compared those two drugs in the same study. So if we were interested in the relative effect of those two treatments, how might we get an estimate, since there's never been a study done? Or here's another example. Mirtazapine has never been compared to bupropion. So it turns out that you can actually get what's called an indirect comparison, since there's no direct comparison, through a common comparator. So both of them have been compared to fluoxetine. So if mirtazapine does better compared to fluoxetine than bupropion does, that might be evidence that mirtazapine is better than bupropion. Likewise, they've also both been compared to sertraline. They've also both been compared to paroxetine. So there are a lot of these indirect comparisons, and we might be able to do a meta-analysis of those to put them together to get an overall indirect estimate of these two. And therefore, we'd be able to do this analysis. And in fact, they did this in this particular study, and they found an odds ratio of 0.79 with a confidence interval of 0.7 to 1. Here's another example where this particular comparison actually has been done. So there is a direct estimate comparing milnacipran to fluoxetine, but there's also indirect comparisons through many of the other drugs. And so we might want to say, well, what if we combine the direct estimate with the indirect estimate? Then we might get an even better estimate of the effect. Because, for example, if there was only one study here, but there were 15 other studies that included one of them, then we might get improved precision. So in this case, a meta-analysis of these two treatments came up with an estimate of 1.1 with a confidence interval for 0.7 to 1.8. But when we combine that with the indirect evidence, the multiple treatment meta-analysis, the mixed effect meta-analysis gives you an estimate of 0.97 with a confidence interval that's a little bit smaller because you now have more precision because you're using more data. Another very common type of network is what's called a star-shaped network. So this is a network for second-generation anti-epileptic drugs. And you can see that in each case, one of the drugs has been compared to placebo, treatment H. So there's a whole bunch of drugs which have been compared to placebo. Presumably these are company comparisons for licensing, but none of the drugs has ever been compared to each other. So in this case, the only way that we can compare the drugs to each other is by comparing their relative efficacies relative to placebo, right? So all we have here are indirect effects. So the idea of the network meta-analysis is to combine the direct and indirect estimates of the multiple treatment effects in such a way that you respect the internal consistency of the graph and respect the randomization that you have in each of the studies by estimating the effect of each intervention relative to every other, whether or not there's a direct comparison, and to calculate the probability that each treatment is most effective and to rank order them in order of their efficacy or safety or whatever the outcome is. Yeah.
If you have a situation where B is better than A and C is better than B,
yes.
Is it possible to have a situation where C is not better than A?
Oh yeah, sure. So one of the assumptions, so the assumption I'm going to make is something called consistency. which is that basically it's kind of like an additive effect that A plus A to B and B to C is equal to A to C, but that may not hold, right? There could be a variety of reasons where. Yeah, I'll give a couple of examples later. So one would be, let's say that A is a placebo and B and C are company drugs, and so each company compared their drug to placebo, and so it turns out that company B did better than placebo, but company C did even more better than B, right? So C is better compared to A than B is. So it looks like C is better than B. But when B and C were actually compared, the comparison was done by company B, and they set up the test so that their drug was under ideal conditions and the other company's drug wasn't under ideal conditions. And so it turns out that B was actually better than C. So that's what's called a sponsor bias. But it could also happen by chance. Yeah, I mean, we've got some examples like that in the literature where those things happen. Okay, so here's just a very simple graphic to show you what's going on. Let's say I have 7 trials that compare A, B, B, C, A, C, or in one case we have all 3 compared. And I'm interested in the comparison of A with B. So how would I do that? So I have direct evidence from trials 1, 2, and 7 that all compared A with B, and I have indirect evidence from 3, 4, 5, 6, and 7 that all compared A or B with C. So one way I could do this is I could do the naive thing of just combining all the A arms and comparing it to all the B arms, right? So take the data from trials 1, 2, 5, 6, and 7 for A and compare it to the data from trials 1, 2, 3, 4, and 7 for B. But the problem with that is that's sort of like the mistake we made this morning with the Simpson's paradox, because I'm now not respecting the randomization. The A-B comparison is valid within trial 1, but it's not valid across different trials because I'm combining different groups. In particular, let's say, for example, that trials 3 and 4 had particularly unhealthy individuals, so the event rates were very high. And trials 5 and 6 had particularly healthy individuals, so the event rates were low in both groups. Then on average, the A's would be better than the B's, but just because of what trials they were in, not because they were actually better. So what I'm going to do instead is I'm going to use the indirect evidence of A versus C versus B versus C as additional evidence to add to the direct evidence of A versus B. And so I can only do that if 3 and 4 are really comparable to 5 and 6. If 3 and 4 are very different from 5 and 6 in such a way, in certain ways, then I'm not going to be able to make those comparisons. But as long as the BC comparison in 3 and 4 is, and one of the assumptions that I'm going to make is that had I done A, I would have gotten the same result as I got in trials 1 and 2. Then I'm okay to make that comparison. So let me give you an example here. So let's say we have trial 1, and trial 1 compared A with B, and A is the placebo and B is the treatment. And the blue area indicates the treatment effect, the difference between A and B. And then I have trial 2, and I compare A with C, and red is the treatment effect. So if I now take the difference between the C arm and the B arm, the C arm in trial 2 and the B arm in trial 1, I get this difference here. But that's not the right estimate that I want, because there's a different baseline level in these 2 trials. If I'd raised this baseline level from in A up to where it was here, this would have been raised. And actually what I want to take is the difference of these 2 differences. In other words, the difference between this and this minus the difference between that and that, not the difference between the 2 arms themselves. So it's invalid here because the study effect differences are not acknowledged and doesn't account for the differences in the placebo. So instead, what I'm going to do is I'm going to say that the A versus B effect and the B versus C effect can be combined and added together. So if you think of this, hopefully everybody here has seen sort of vectors in some form, but if I go from A to B, and then I go from B to C, then as long as this triangle works, that's the same as going from A to C. So A to B plus B to C is equal to A to C. And that's what this says here. The effect in the AB trials plus the effect in the BC trials is the same as the effect in the AC trials. That's the consistency assumption. And therefore, and I can calculate a variance as well, because these are independent. So here's an example where a network was done where one of the treatments was toothpaste, one was gel, and one was placebo, and the outcome was cavities. And it turns out that there were 69 studies that compared toothpaste with placebo, 13 that compared gel with placebo. The standardized mean difference for the placebo versus toothpaste was a reduction of 0.34 standard deviations, and placebo versus gel was a reduction of 0.19. And our question is, well, how do we compare the toothpaste and the gel in that case? So both of them work better than placebo, and the toothpaste seems to work a little bit, has a bigger effect than the gel. And so we want to know how to make that comparison. So the obvious thing to do is just to take the difference between the 0.34 and the 0.19 and to calculate the sum of the variances. And when we do that, we find a difference of 0.15 with a standard deviation of, or standard error, I think that's actually a variance, of 0.0037. Now, this was actually part of a much bigger network, which included several other treatments. And so we might be trying to figure out how to use all the other indirect evidence that's available in this particular network. So the basic idea here is that you have a direct comparison of A with B and a direct comparison of A with C, and you therefore can get the indirect comparison of B with C from the difference in the two. Okay, here's another example. We have a network here where we have treatment A and treatment B compared in trial 1, treatment A and treatment C compared in trial 2, and treatment C and treatment D compared in trial 3. So the blue area here indicates the treatment effect in trial 1. The red area is the treatment effect in trial 2. And the blue area here is the treatment effect in trial 3. Now, what's the relative effect of, let's say, so we know what A versus B is, that's right here. What's the effect of C versus B? Well, here's the effect of A versus B. Here's the effect of A versus C. And so the difference is the effect of B versus C. Here's the effect of this is C versus D. And this is C versus A. So this whole sum here is A versus D, right? And likewise, this would be C versus D versus B, okay? So we're just basically combining these things together. We're using these connections to say that B versus C is just the difference between these two, and A versus D is just going to use the fact that we've compared A with C and C with D to get an A with D this way, and then we can combine the A with B to get a B with D. So basically, the estimates are said to be consistent if the indirect and the direct are the same thing. So in this case, we have a comparison of A with C, which has a 10-point difference, a comparison of B with C, which has an 8-point difference, and therefore the indirect estimate is 2, because that's the difference between the two. But we might have found a direct estimate of 1.9, and in this case, the direct and the indirect are pretty close, and so we'd say they're consistent. And therefore, we can combine them all into one model. Mm-hmm. Yep. Yeah. Yeah, so this, okay, so this is C compared to A. So think of A as 0 as the baseline. So this is the effect of C. And then this is the additional effect of D versus C. So that goes on top of the C, right? Because C is stopping right here. So this is D versus C. Here, let's actually, I should do it. This is C, right? And then this is the additional amount of D versus C. So A to C plus C to D equals A to D. All right. Okay, so in this case, we have consistent estimates, but in this case, we expected a difference of -2, but we got a difference of +5 when we did the direct study. So they would be inconsistent, possibly. All right. So how do we, and this is going to be a very complex model, but I'm just going to give you a really simple way of thinking about how to combine these estimates. Well, you could have different. I'm gonna get to that in a minute. You could have different. You could have different effect modifiers operating in the different studies. Like, in other words, the people who were compared in the A/B studies are different from the people who are compared in the BC studies. So if you go back here, you know, you could, yeah. I mean, it could be a lot of things that could cause it. It could be that the people in these kinds of studies are very different from the people in these kinds of studies, and so it leads to different effects. Sometimes you'll find that, like maybe let's say C is the original drug or the original formulation, and B and A are new formulations, and so these studies were done before this study, and things have changed over time. And so the other standards of care have changed. And so now this treatment is not as effective. Remember back to the magnesium, and I said that magnesium is effective by itself, but not in effect with others. So
I had an example with infection one time, and I had a pain with the disc, and I took one medication that was basically Tylenol with codeine to kill pain. I also took a muscle relaxant. So what I did is I took the two together, thinking it would be good, but what it did is threw me into a state of depression. Yeah.
So there's, well, I mean, so that's a situation where you're doing a complex intervention. I mean, if you thought of A as a combination treatment, then it might be that each treatment worked on its own, but together they don't work very well. That wouldn't necessarily really be this kind of situation, though. This is really a situation where you have different treatments that are being compared in different studies. So this sort of thing can arise when, so let's say, for example, that yeah. Right. If you think of this as a combination treatment, yeah. I mean, another situation would be if, so let's say you could only people who didn't have heart disease could take treatment B, but treatment A could be taken by anybody. Then this BC comparison is only going to be in people who don't have heart disease, and likewise the AB comparison will only be in people with heart disease, without heart disease, because B is contraindicated in those cases. But this would be in everybody, so that might be a situation where you get an inconsistent effect because the groups of people in the studies are different. So one way to think about how do we estimate this sort of mixed treatment comparison is, well, we can take a weighted average of the direct and the indirect estimates. And for those of you who've done any Bayesian analysis, you'll see this as a shrinkage type estimate where we're weighting by the inverse of the variances. So the mixed effect here is an average of the direct effect and the indirect effect. And so in the gel toothpaste example, the indirect effect was minus 0.15, the direct effect is 0.04, and therefore the mixed effect is an average of those two, averaged, weighted according to the inverse of the variances. So notice that the mixed effect has a smaller variance than either of the individual effects, and so that's a gain in precision, which we get just because we're using more information. The difference between the direct and the indirect effect is 0.19, and we can actually calculate a confidence interval on that. And we could say, well, for example, the inconsistency there is almost significant if you want to think of significance as being whether or not the inconsistency factor includes 0 or not. If it doesn't include 0, then it would say that the difference is different from 0, and therefore there might be an inconsistent effect. So that's just a very crude way of kind of thinking about how to combine direct and indirect effects and test for whether they're different. So here's another example where we have a closed loop, and the loop meaning that I can go between any node. So I can use trial 1 to go from A to B, and trial 2 goes from A to C, and trial 3 goes from B to C, and so I can make it around the loop. And so the colors there represent the effects in each trial. And so now the indirect effect between C and B is the difference between AC and AB. And the direct effect is the purple, the difference between C and B. And you can see in this case that this is consistent because the direct and the indirect effects are the same. On the other hand, here's a situation where there's an inconsistency because the trial 3, which gives the direct effect, has a bigger effect than the difference between trial 2 and trial 1, which gives you the indirect effect. And one of the causes of this could be that the populations in which these trials were studied differed. So for example, with trial 1, it might have been a population that was moderately sick. In trial 2, it's also a moderately sick population. So therefore, the indirect estimate is relative to a moderately sick population. But then when the direct effect is done in a population that's only mildly sick, and so you get a different effect because there's a treatment interaction there that's related to the sickness that the person has at baseline, and that's not being reflected in the mixed treatment comparison because you're basically combining two different subgroups. So there's a sort of a fundamental issue here, which is called transitivity or exchangeability. And the basic idea is that fundamentally what network meta-analysis is a missing data problem, right? Because if you have a network where not all sets of treatments are compared in each study, that means you have missing treatments in each study. So if I have an ABC network, the AB trial is missing treatment C, the BC trial is missing treatment A, the AC trial is missing treatment B. So basically this assumption of transitivity means that the effect of treatment C is similar whether it appears in the AC or the BC trials. So if, for example, treatment C is given differently in the AC trials than in the BC trials. For example, it's given as a high dose in one and a low dose in another, then you would have a situation where you might have some inconsistency because these studies are not exchangeable. Another way of thinking about this is two sets of trials, AC and BC, do not differ with respect to their distribution of effect modifiers. In other words, the factors that might lead to treatment interactions might be different in those sets of trials. One set of trials might be done in older patients, one might be done in younger. And so if those are different, then you can also get some problems with these assumptions. Another way of describing this assumption is that participants in the network could in principle be randomized to any of the three treatments. If they can't be randomized to some of the treatments, then some of the comparisons won't be valid because you won't be comparing the same types of people. Another way of thinking about it is that the treatment that's missing in each trial is missing at random, possibly conditional unknown variables. And another way of looking at it is that there are no differences between the observed and the unobserved relative effects of the AC and the BC beyond what can be explained by heterogeneity. And so another way of thinking about this is if I think of the effect of comparing treatment X with treatment Y in any given design D, that effect is the same no matter what the design is. In other words, if I compare A with B, it doesn't matter whether I do it in an AB trial, an ABC trial, or I do it indirectly between AC and BC. The effect is the same. If that's the case, then I can do this network analysis. So what are some examples here? What if C is standard care and A and B are different generations of drugs? Then the standard of care may have changed over time. And so therefore, even though it's standard care, the standard care in the AC trial may be very different from the standard care in the BC trial. And so that might lead to inconsistency. Another example is, what if the AC studies have a higher proportion of very ill patients than the BC studies? Then when I start combining them together into an indirect comparison, I'm combining estimates from two different sets, and they may be very different. And finally, what if C can only be given to certain types of people? Then I certainly couldn't have randomized people to any of the treatments. People who can't get C can't be in any trial with C. So if we think about 3 studies, one of which is AC, one of which is BC, one of which is AB, and we think about 3 estimates that I get in those studies, then we could fill this in by saying, well, what if in the AC study I also had R&B? Then I would have also got a BC effect and an AB effect. So in this case, the black are the effects I observe, and the red are the effects I'm missing. And the idea here is that these AC studies should all be drawn from the same distribution. Likewise, the BC effect and the AB effect. So if this observed effect is different from these in terms of coming from a different distribution, maybe because they have different effect modifiers or for some other reason, then these assumptions are not going to hold. All right, so the basic assumption is that if I'd done this trial with if I'd done the complete trial, then I would have gotten effects coming from the same distributions. All right, so here's an example of imbalances caused by different effect modifiers. So one of my colleagues gave this example, and I kind of like it because I think it makes it pretty obvious. So let's say we did a study of cars, and we wanted to see how well they drove on ice. And so we compared a Porsche versus a Golf, and the Porsche was actually 2 seconds faster on the course than the Golf. Okay, and then we did another study where we compared a Volvo versus a Golf, but this time we did it, and the Volvo was 8 seconds better than the Golf. And so therefore, the Volvo was better than was 8 seconds better than the Golf, and the Porsche was only 2 seconds better than the Golf. So therefore, if I did the indirect comparison, the Volvo should be 6 seconds faster than the Porsche. So the question is a Volvo faster than a Porsche? Now, before I go to the next slide, which of course you probably have in front of you, but what do you think is the problem here with this indirect comparison? Yes, so we're comparing one in ice and one in dry conditions, right? So in other words, the effect modifier here is the weather condition. And so it's not fair to say that that one is better than the other, because that's a potential biasing effect. It might very well be that the Porsche is going to be much better than the Volvo on, or let's put it this way. If the Porsche had been compared to the Golf on the dry track, it might have done much, much better. And likewise, if the Volvo had been compared to the Golf on the ice, it might have done much, much worse. So we don't necessarily know that. So if we're going to assume that there's an indirect effect here, and we're going to actually estimate that the Volvo is better than the Porsche, then we're making the assumption that the weather conditions are not an effect modifier here. They're not affecting what's going on. So what are some of the potential causes of this inconsistency where the indirect and the direct effects may not agree? So one is that there's an inappropriate common comparator. That's like the standard of care example where it's changed over time. And so the placebo is really not the same placebo. Another one is that the trial characteristics might have affected what's going on. So one study was done in older people, one study was done in younger people. Another possible reason is that the comparators might have changed in definition. So again, what you call standard of care might have changed. The trials might have been including different populations. And empirical studies show that inconsistency is not that uncommon, at least in some loops of networks. So there are going to be a variety of different diagnostics that you can use to test for inconsistency. And what you'll find, particularly in bigger networks, is that there's always some inconsistency somewhere, but it might not be enough to really make a big difference in your analysis. So how do we analyze inconsistency? Well, there's a variety of ways of doing it. I showed you one where we compared the direct to the indirect via z-test, and that's called the Bucher method. You can also look at different loops and see whether the indirect and the direct estimates are the same. There's a method called node splitting, which you can also use by basically taking one of the nodes out of the network and recomputing things. And there's also various modeling techniques using global methods where you put factors into the model that are inconsistency factors. Again, I'm not going to have a lot of time to describe all those, but just to show you a little bit about how these models are fit, returning to the toothpaste example, let's assume that placebo is our base treatment here, and so we can compare placebo to any of the other treatments. So that gives us a direct comparison, and then the toothpaste versus gel is a function of those according to our model. So the toothpaste versus gel is a function of the toothpaste placebo and the gel placebo. And we can generalize that to say that the placebo comparison with any treatment is a base parameter, and all the other parameters are functions of those base parameters, so that there are really only 5 degrees of freedom here, because there's only 5 of these edges that we need to estimate to be able to come up with all the others. Yeah.
When you've done studies and you found out there's a real inconsistency, what should come to that conclusion? What have people want to study?
Well, so I'm going to talk a little bit about that later. So let me hold off on the answer to that. As an example, let's say we have 3 treatments and treatment A is the reference. So therefore, B and C relative to A are the basic parameters. And then BC would be the functional parameter. And so the choice of which parameters to use as the basic parameters is arbitrary as long as they form what in graph theory is called the spanning tree. And so some of the software actually computes that for you automatically. You could also model the treatment arms if you wanted rather than the contrasts. Just like in the meta-analysis that we've talked about, we can analyze the contrasts as the differences, or we could look at the arms themselves in the one-stage models. You can express a network in some cases by a meta-regression. So for example, let's say we had 3 studies. Study 1 compared A with B, study 2 compared A with C, study 3 compared B with C. We could set up 2 dummy variables, one of which represents the AB comparison, one of which represents the AC comparison. And the third study, which is BC, well, BC is equal to AB minus AC. And so therefore, the AB parameter x1 gets a 1, and the BC AC parameter x2 gets a -1. And so now we just model this as 3 observations with this design matrix, these parameters, and then you can put in random effects if you want, and model that by a generalized linear mixed model. If we had multi-arm trials, so in other words, let's say we had a trial comparing P with T, P with R, T with R, but then we had a 3-arm trial that compared P with T with R, then we have a PT estimate, a PR estimate, a TR estimate, and then we have these 2 estimates, but since they're in the same study, they're going to be correlated. And so we have to induce a correlation here. So we not only have 2, we have the 2 data points, which are the Y's, but we have their variances, but we also have the covariance. And so we could model that this way. So notice here that study 4 has both an AB arm and an AC arm because it's a 3-arm study. And so notice that we have 2 deltas here and 2 epsilons, which each are relative to study 4. And so therefore we have a correlation induced in that study. And so Y1 in the AB study has a variance, Y2 in the AC study has a variance, Y3 in the BC study has a variance, but Y4, AB and AC have 2 different variances as well as a covariance, a correlation. And so that would be a correlation in the observed effects, and we could also have, if we had random effects, we could have a correlation in the random effects here as well. And so we can fit this using mixed models. And so again, this is just a standard mixed model analysis where we say that Y is equal to a design matrix times some fixed parameters mu, and then there's some random parameters delta, and we have 2 components of variance within and between, and we can just do the mixed model analysis here and estimate all these parameters. So the problem here is that you oftentimes will have networks that are very sparse, meaning that you have a lot of treatments to compare, but there's a lot of combinations that have never been compared or have only been compared once or twice. And so there's not a lot of information about these connections. And so that can lead to either difficulty in fitting the models or just a lot of imprecision, a lot of large standard errors. You also have the trouble that multi-arm studies have all these correlations, and so you have to account for those correlations. So oftentimes these models are simplified to assume that all the variances are the same. So that, for example, tau squared AB and tau squared BC are the same. And you also, if you make that assumption, you also have the assumption that the correlations all become a half. So here's an example where we have an AC study, an AB study, and a BC study. It's a 3-arm study. So therefore, and we're going to assume that the variances are all the same. And because of the fact that these variances are the same, and because of the consistency assumption that the difference in these 2 is equal to that, what happens is that you can show that the correlation between these 2 things has to be a half. And the next slide, I've actually shown you how to prove that, but that's not that important. The important thing is that if you make this homogeneous variance assumption, you induce this correlation of a half. And the reason I want to make that point is because most of the network meta-analyses that have been done have typically used this assumption. So they're assuming a homogeneity of variances. There are now some new models out that allow you to kind of get rid of that assumption, and they'll probably becoming more popular as we go forward. And typically what the software does is it will split the multivariate problem into 2 conditional univariate problems in order to be able to fit it with the standard software. Okay, so what at the end, when you fit all these models, what do you get? So what you get is an estimate of the odds ratio comparing any pair of treatments with any other pair of treatments, again, under the assumption of consistency. So here is the result for the depression studies. So in each row, in each column, you can see the comparison of the 2 treatments. So for example, this is citalopram and bupropion. And the upper triangle gives you the dropout rate, the odds ratio for the dropout rate, which is kind of the safety outcome. And the lower triangle here gives you the efficacy outcome, the response rate. And so if you look at these data closely, the numbers that are underlined are the ones that are statistically significant, where the odds ratio doesn't include 1. And you can see generally that in the column REB, I think it's reboxetine, that all of the other treatments are better than reboxetine. So all of those are underlined and bolded. So reboxetine has worse efficacy than all the other drugs. And sertraline actually seems to have worse acceptability than a lot of the drugs. But anyhow, the point is here that you sort of get an estimate of everything. And you can see from this that some of these are much more precisely estimated than others. So if we go back to the original diagram, I think mirtazapine was one which had very few studies. And you'll notice that the confidence intervals on mirtazapine tend to be much wider than the confidence intervals on say, fluoxetine, which had a lot of studies. We can also rank the treatments. So one way of thinking about this is that if you did a Bayesian, many of these are Bayesian analyses. If you did a Bayesian analysis, each simulation gives you an estimate of the comparison of any treatment with any other treatment. So you can use that to rank order the treatments in terms of their efficacy. And then if you accumulate that across all the simulations, you can get the probability that each treatment is ranked first, second, third, and fourth, and so forth. So here's a hypothetical example where we have 4 treatments and 4 possible ranks. And so, for example, here this says that treatment A has a 1/4 chance of being ranked first, 1/4 chance of being ranked second, third, and fourth. Treatment B has a probability 1/2 that it's ranked 1, 1/4 2, 1/4 3, and so forth. And then over here you have the cumulative probabilities. So if I look at 2 of the treatments in our network, this is escitalopram. There's a 30% probability that's ranked first. There's a 35% probability that's ranked second. There's about a 20% probability that's ranked third, a 10% probability that's ranked fourth, and very little probability that's ranked 6 through 12. So this treatment is actually pretty good, right? It tends to be ranked in the top level. There's a high probability that's ranked first, second, or third, whereas fluoxetine tends to be not so good because it's peaking at a rank of about 8, 9, or 10. So we could actually average the rank here under this distribution, average the rank here. And it turns out that the area under these curves is proportional to the mean rank. And that's called the cumulative area under the curve. And I'll show you that in a minute. Here is another way of displaying the data. So this is for all 12 outcomes. And I've shown the efficacy and the safety on the same plot. So for example, here, reboxetine, if you remember, was kind of outpointed by all of the data. And you can see that here, that it's ranked near the bottom with a high probability for both outcomes. Whereas escitalopram is actually ranked pretty highly on both outcomes. Venlafaxine does pretty well for efficacy, but it's not doing very well for safety. So it tends to make people better, but it also makes them drop out of the study. Mirtazapine is really good. It's very effective, but it also has a pretty bad safety profile and so forth. And then if you take all these ranks and you accumulate them, so this is the cumulative ranking curve. So what this means is that there's about a 60% probability that paroxetine is ranked in the top 8, and there's about a 40% probability that's ranked in the top 7. And the area under the curve here is 0.35 or 35%, and the area under the curve here is 0.77. And so treatments that have a much higher area under the curve are much better because they tend to rank toward the bottom rather than toward the top. Whereas reboxetine has a very bad rank because it's almost always last. And it turns out that the area under the curve, which here's the formula for calculating it, it's a function of the mean rank. So the mean rank, the average rank here for each of these studies is equal to the number of treatments minus the area under the curve times the number of treatments minus 1. You can show that. So in other words, what this network meta-analysis has allowed us to do is it's allowed us to rank the treatments to get comparative estimates of all pairs of treatments and estimates of uncertainty without having observed every single comparison. Okay. Questions on that? So I usually teach a whole day course on this. So if that 30 minutes didn't do it for you, it's only an introduction. But there's an awful lot of literature on the network meta-analysis now. It's becoming much more common in the clinical literature. I think there's several hundred of them done every year. And a lot of companies are doing them now because they are using them as ways to figure out, how their products compare to other people's products. So it's a useful technique. Yeah. Mm-hmm. I mean, you could. I mean, it's right. Well, like in any statistical analysis, when you find some kind of an outlier, right, you have to figure out a reason for it, and it's kind of hard to know which one to which to say. People like to jump to conclusions like that because they're easy to come up with, but I don't know. All right, so we're kind of at the end of this stuff. What I've left on the last couple slides here is some books and papers if you want to look at. So there's a list of kind of textbooks on meta-analysis that have come out over the last few years. The one at the bottom is the one I'm working on with a couple of colleagues, which is going to be coming out in the statistical press, hopefully whenever we finish it, maybe this year, maybe early next. And then the last slide has some references for network meta-analysis, which, as I say, is kind of a newer technique, but there's some nice books out on it now. And there's a group of people who are really doing a lot of work in that, and that's who these authors typically are. So I'd recommend all these materials. The evidence synthesis site. Yeah. Yeah, sure. Yep, I'm happy to do that. Let's see. Yeah, so this is our website, evsynthacademy.org. So it's got a little blurb about, who we are, and this is our team, little biographies of each of us. We have a bunch of courses that you can take that are online here, and how to contact us and so forth. Some of these courses actually have little exercises in them that you can take and you can get graded on. This was one of the videos that I was telling you about, the steps of a systematic review. We also have a video on the forest plot. The introduction to evidence synthesis is just kind of an overview for non-technical folks. And then there's sort of a separate module on each of the topics that I covered yesterday. And then we also have we have an R module and an abstractor tutorial module. And we also have some slides on study design and data analysis. So if you're interested in those, you can also get our software from that site. And I think actually you can actually get to our, you'll be able to get to our center site as well. Okay, you can get to the Brown site, and then if you go to research, let's see. So you can get to the Center for Evidence Synthesis and Health here. And you can actually get to the to Evidence Synthesis Academy through this as well. But this is our website. So this has some examples of our systematic reviews and our software. So see, these are some of the, I actually haven't looked at this myself. So let's see what you get when you open this up, urinary incontinence. So these are some of the contracts that we've done for the government. So the question is, what are the best non-surgical treatments for urinary incontinence in women? Here's what our team learned after reviewing 251 research studies. This probably just takes you, just takes you to the AHRQ website, to the Effective Healthcare Program, and you can download this report. So if you want to see what one of these reports actually looks like, with all the stuff that we've learned, you can look at that. Go back to the Absinthe Academy site and just show you like some of the introduction course, which you can do without signing up. We have a menu here on the left. What is evidence synthesis? And then we have some text and some graphics. Why is evidence synthesis helpful? And so forth. So you can just, I mean, a lot of this I've probably already said, but if you've got colleagues who are kind of interested in this, it's sort of a little introduction, to what the topic is. Well, we're not going to have the grant for a long time, but this is going to be up there no matter what. Yeah, we're actually still talking about how we're going to maintain this. I mean, this stuff isn't going to go away, but like, are we going to develop some new stuff, or Yeah. Well, for the open meta-analysts, we are. The SRDR has been updated, and the abstractor is currently being updated. And so that actually runs automatically. Let me see actually if I can. Let's see, under software. I'm gonna try it down here. Okay, let's see if mine still works. I don't know. Let's see. I haven't used this in a long time, so I don't remember what my password was. Oh well. I was going to try to demo it for you. I wonder what happens if I choose a root. No. Oh well. Yeah, this is a standalone. This is a standalone. So basically, if you don't have an account, you have to register here. So I guess I could try to recover my password. Let me see if they'll take my.
Sorry, while you're doing that, what did you just say that all three of these are going to be web-based, or one is?
Yeah, well, they're all. So yeah, they're all going to be web-based. All right, so there's my password. Well, keeps wanting the default here. Why does it? So let me in. Huh. I don't know what's going on here. Try one more time. Nah, I don't know. For some reason it's not letting me in. But yes. Well, no, right now the abstractor and the SRDR are web-based.
Okay.
The Open Meta-Analyst is the one. So I could actually demo Open Meta-Analyst. Let's see. No, the abstractor isn't, although I think they have some funding for that. The Open Meta-Analyst is not either. Let's see, what happened to the software here? Let's try here. Yeah, so this is the Open Meta-Analyst program. You can download it. I've actually got it on the computer here. So I could just run it for you quickly. I mean, it's pretty easy to run, and it does all the basic stuff. It's just that we haven't really updated in a long time. It's based on Metaphor. It's basically a GUI wrapper for Metaphor in essence. So let's see here. Let's open a recent project. So I'll open the Bcg data that we just analyzed. So for example, here's my data set. And if I want to analyze it, I could say I want to do a meta-analysis. I want to do a binary random effects model. Let's say I want to use the restricted maximum likelihood. I'll say OK. And hopefully it'll run. Okay, so there, let's see. We have an estimate of 0.475, confidence interval 0.33 to 0.68. So that's what you just saw on R, because it's basically just mimicking the Metaphor package. It's just calling Metaphor. So you don't have to put in all the commands. You can just do it from a menu. And then if you want the forest plot, here's the forest plot. Or you could do it. You can do a meta-regression with it. It just doesn't do as much stuff as we'd like it to do. And right now you need to download either a Windows version or a Mac version. And the problem is that we don't always, we haven't been keeping them up to date. So every time a new operating system comes out, we get emails from people saying we can't use it. And the whole point of going over to the web was so we wouldn't have to keep doing this. So I think they run. Yeah. No, this is standalone. R is built into the download. Yeah. So, yeah. Any other questions? All right, we did it. All 522 slides.